speed based on your latitude.
Correct.
Uh, so I was listening to yesterday's stream and enjoying it significantly. What I noticed is whenever I make funny voices, it's really funny. I should make more funny voices. Like crazy voices, like just being silly. Like just being silly is really funny. Apparently. Anyway, let's copy. There you go. There you go. All right. So, connects to the internet. All right. So, yesterday, what did we end up? So, I ended up, let's just correct yesterday's, the name of the video. I ended up debating Fligalulu. Fligagigu. There he is. 4 subscribers. Debate with Fligagigu. Racism. Racism and rationality. What else? Am I who is the top who is the world's top super nanny economist? What else did I say? Not who is, but am I the world's top super nanny economist? And economist. 100. Okay, that's it. We're done. It is good. Give me more. I shall have more of this drink. What do you call this drink? It is coffee. I like this drink. It's good. It is good, this drink. I'm still looking for that part of his course where he explains. What am I don't even remember what I'm looking for. Where he explains. What am I looking for? Where he explains. It's gonna come back to me because it's something that I always need. I don't remember.
Everyone has an intuitive understanding of what the viscosity of a fluid is. Honey.
Okay, I think we understand enough of viscosity at this point. What did I just do? Jesus. Let's try this again. Okay, so we looked at this lecture and we solved the problem with the skids. So we're good to go on.
Burning too many fossil
Okay, let's hear this. This looks interesting.
fuels, yet they're bringing things at larger scale. They're all yapping on about global warming, burning too many fossil fuels, yet they're bringing things at larger scale. It requires just absurd amounts of power. Maybe they have to create the hurricanes to fuel power the windmills. Yeah.
One thing that we know that intelligence will do is fake conspiracies. That's the real conspiracy, right? Because it's actually true. You seed you poison the well of investigation to make it so that no one. Let's say a politician committed some crime, and you've got people all over the internet and they're digging into it. You're like, okay, what do we do to stop this? To make us look bad. They intentionally seed believable but misdirection. People start chasing after the misdirection, thinking they found something, and they end up in the middle of nowhere, never uncovering what really happened.
Oh, I think there's something probably worse than HARP, and HARP might have been something serious. Because I don't think the government even really operates now. It's the University of Feds, right?
I try to tell people that when a lot of people bring up HARP, and I'm like,
HARP is like an idea. It's a thought process of a very powerful type of technology, but it's old. And I think it's possible that, the whole term is being used as a distraction now to discredit people who talk about it. I do think there's a technology that's bigger than HARP that can do exactly what HARP conspiracy theories are saying that it does, though.
There's also lots of harps.
Yeah, there's a lot. It's not
just
Alaska.
this one,
Exactly, there's a lot of
harps. And if you think,
I don't know what they're talking about. Don't know.
of the modern world,
Don't know. Don't care. Let's try this.
a futuristic city rising in the middle of a
So Dubai we looked at yesterday. We're done with that.
Variant and covariant tensors. Specifically, we're going to talk about tensors of rank 1, so vectors, in this video and the next, after which we'll explore.
Yeah, we need to. So I'm beginning to understand covariant and contravariant, and the reason I'm beginning to understand it is from actually this guy.
Here's a second order tensor. We saw it.
No, not this guy. The other guy, the Eugene guy. He had a good video, but let's watch this again.
The previous episode is constructed over two vector spaces shown as blue and red. We also saw we can visualize it as a sphere with arrows.
Oh, it's part 2. Okay.
We can interpret the sphere as a kind of a map between the two spaces. Given a blue vector, we can feed it into the tensor and obtain a red vector.
Let's watch the part 1 again. Oh, there's 2B. Where's 1? Maybe we can just go back to 1.
Let's start with vectors. Vectors are usually visualized as arrows. A vector has a length and a direction. We can also specify a vector using a list of components or coordinates. This vector's components are 2 and 3. It means its size is 2 along the x-axis and 3 along the y-axis. In this video series, we'll add the labels of the axes inside the component list. This will help us later. Here are a few more examples.
Hey, that's nice. That makes it a tensor. That's so nice. This is now you see that it's tensor of rank 1. There's 1 basis vector. This is terrific.
Example vectors with their component lists. Vectors reside in what's called a vector space. This one is 2-dimensional, so it has 2 axes, and each vector is specified using 2 components. Here's a 3-dimensional vector space. In this space, there are 3 axes, and each vector is specified using 3 components. Now let's take 2 3-dimensional vector spaces. We gave them different colors to distinguish between them, and also label the axes of the red one using capital letters. And here's an example tensor. It is a 3x3 matrix having a total of 9 components.
So the X is small. I mean, the first one is blue and small. The second one is red and big. So these are the lowercase. These are the uppercase, red uppercase. It's not a good idea to separate by color and by size, like, because now you're confusing me. Like, well, now that I noticed it, I see there's no reason for this. Either choose small letters, big letters, or different colors. Don't confuse this with both different colors and different sizes letters. Okay, so this is a matrix. No, it's not a matrix. This is not a matrix because there is very specific information here. So 2.3 in the X, in the blue X, and the big red X. So it's 2.3 in this direction and in this direction, whatever that means, some abstract notion, 2 directions. So this is a tensor of rank 2. So can this describe stress? A stress tensor is very specific. It describes some pull or push, but some shear and two shears. So pull, push, and 2 shears, or tension, shear on each face. So the face, the direction of the stress. The face, the direction of the stress. You might as well call this, instead of red, say the direction of the stress, the face. So there's we could say either 3 faces or 6. How many faces are there here? Either 3 or 6. And again here, so each. So here there's, you could say, 6 directions. Positive X, negative X, but when it comes to each component, you want to ask, right? It's basically a point. At that point, if we slice in the X direction and we look at the X face of the point, what is the X direction stress? What is the Y direction? What is the Z direction? And again, we'll ask that for the y face, and for the z face. And that should be enough. So this is for the x, there's 3 stresses. For the y face, there's 3 faces. And for the z face, there's 3 stresses. So this should be enough to describe the stress tensor, the Einstein stress metric. Not a metric, it's a tensor. I don't know what a metric is. We'll come back to a metric. All right, pretty simple. Not complicated. I mean, I've known this for many years. I just didn't know, and I've known about tensors for many, many years. Just that I didn't realize that they are such mathematical like objects with so many rules. Like I've never looked into the rules that govern their transformations. I've never had to transform them. But apparently they're very useful. They have this, they maintain this compulsory intrinsic behavior or definition under transformations. That's the power of the tensor. For some reason, I don't know. I mean, the word sounds like it comes from engineering. But all of math comes from engineering. Math is just engineering. Like 1 + 1 = 2. That's engineering. You might think that that is pure math. There's no pure math. All math is some it's some notion of the world. You can't talk about anything unless it comes from this world, from some experience. So 1 + 1 = 2 is just an experience. We've all experienced that 1 + 1 is 2. And we've all experienced that 2 × 2 is 4. And so on. We've all experienced that 2 to the 2. What is 2 to the 2? 2 squared. Oh, that's also 4. And so on. We've all experienced all these things. We've all experienced probability, and we've all experienced, I guess, statistics. Statistics, I think, is more definitional than. I mean, it's applied math to some definitions. Unlike probability, probability is more scientific. What is statistics? I don't know. Yeah, like the average. That's just a mathematical definition. There is no average in the universe. No, there is no such thing as average. There is no that well, but there is no height either. There's no humans don't have there are no humans in nature. Humans, like, it's a word the way we define whatever a human is, whatever we feel like, however we feel like defining it. Wait, we didn't do audio test. Jesus, that is ridiculous. Oh, thank God. Audio pass. Redonkulous. Thoroughly redonkulous. I don't accept it. Okay, the audio stress test has passed. So it has come to pass. So, yeah. So one thing I feel like it's good to slow down. Like I've noticed that tensors are giving me such a headache. So I'm just slowing down because I see that every time I speed up trying to understand tensors, like I have no idea what's going on. I don't want to waste my time just listening to the professor explaining and explicating and what's another word? Expounding and see any other words? And talking and I don't understand. That's a waste of time. I don't want to do that. I want to have a rigorous feel. Like the best part of life, especially when you study math and science and engineering, is not to follow. I mean, it's okay to follow the first time, second, third, but at one point you really want to be able to explain it. That's one of the advantages of having this YouTube channel as I'm studying. And that's the power of debating. So you have to explain things. You're forced to explain. It's really amazing. I love it so much. I love it so much. So much I love it. I love it. Yes. So there you go. This is already a tensor.
We just picked some random numbers for this example, but here
But this is before any transformations. Transformations is when it becomes a little bit more, confusing. And then with the covariant and the contravariant, like I don't, I'm still not sure like the definition. And in the Eugene video, it becomes super super confusing. But we might come back to all these videos because I don't know. I don't even know why tensors are so important. But if tensors ended up giving Einstein GR, but it took him 10 years, so so it could take me like a while. So it's fine. No pressure. I just don't understand how some people teach GR, and when it comes to tensors, they just mention it like fleetingly. And here are tensors, and this, blah, 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 and what? Like, are you out of your mind? Like tensors, I don't. I'm thinking back to the lecture in GR where I started from, and he explained the tensors. I still don't know what he means. I'm still trying to understand what the heck is he talking about. Let's try that again. Let's try it again. But first, maybe we should look at the news. Let's look at YouTube. Whoa, Hot Girls updated. 10 years after Hot Girls Wanted, Rachel Bernard wants to talk. What is that? Is that her tummy? Is she so thin? Wait, notify me upcoming, but it's playing. Oh, it's a
All right, so
trailer.
a few weeks ago, I was on Netflix and I was just cruising through all the thumbnails, and there was this documentary there. It was called Hot Girls Wanted, and I clicked on it. And, it was probably, at least in part because of the saucy thumbnail, I thought I was going to learn something about the sex industry. But it dragged me into this world that I really don't have much background in, and I was frankly shocked by what I came across.
It didn't hit me until I got on the plane.
It felt
That's actually very dangerous.
don't have much background in, and I was frankly shocked by what I came across.
It didn't hit me.
People don't know how dangerous what she's doing is. So a laptop on the bed, it's not cooling. It's gonna heat and overheat and start a fire and kill everybody in the building. This could end up in a disaster. The least that's going to happen is you're ruining your machine because you're overheating you're overheating it, which is weird. I mean, why do these computers allow overheating? Like they should turn themselves off with as soon as the temperature is too high, they should have sensors. These things are very dangerous. These are bombs waiting to explode. There's so much energy packed into the battery. So they should have more sensors. They shouldn't allow themselves to just blow up like this, but very dangerous. Never put your laptop directly on a surface that it can't vent. There's these if you look at the bottom, there's these tiny holes. They must allow air flow. Unless it's a new laptop that is like an iPhone that it's only steady state, and but then the CPU usually needs cooling. I don't know. Be like, make sure that the computer doesn't overheat.
Me until I got on the plane.
It followed the stories of three 18 and 19-year-old women who'd answered ads on Craigslist and sort of got pulled into the porn industry, where at first it was maybe what their expectations were. They were going to have sex on camera, they were going to get some money, and it would go on from there. But the thing about the porn industry, at least at that time, was that you had to make a 3-month shelf life.
Shelf life of a girl, best.
She's not hot. She's not gonna last. She's just not hot. She's okay-ish.
But the thing about the porn industry, at least at that time, was that you had to make a 3-month shelf.
Wait, didn't I tell it to play 2x? It's at 2x, but it's refusing because it's a trailer? What is this nonsense?
Shelf life of a girl.
Yeah, she's really not hot. I mean, she's just almost a fat chick. So, like, I wouldn't. I'm sorry. I would have to pass. She's just not hot. I mean, she's fantastic. I'm sure she's a great person and she'll meet the right guy, but I can't. Sorry.
Best case scenario.
I mean, very nice face, but face is secondary. The most important part is the tummy. I can't have such like, I need the waist to be much thinner. Now, there's actually a way to reduce her waist. I mean, I can reshape her with there's not non-invasive ways to reshape her, but she would have to go through those things. It would take time, but she didn't. She needs to get started soon.
A year tops.
The porn industry wanted.
Yeah, he's not. He's not a scientist. He's not an economist. He's not a statistician. He doesn't know. He is a good source of information, but you actually need to collect data. You can't just listen to what he says. And at the end of the day, she's just not pretty.
New faces, and if you wanted to make a living, at least the way they portrayed it, you got in.
She's not pretty, and you can tell that she's timid, she's shy. And that's probably not. I don't think it's going to work. Like, you actually need to be. You need to be stronger. You need your personality to be stronger. It might be a good experience to work in porn, and some guys are going to hear that you worked in porn and they're going to maybe not be interested. Yeah, I can, I can understand that. But to me, like, if a girl was gangbanged, to me that's like more enticing. Like, that's some men would find it more attractive that she can handle, let's say, how many? Let's say 4 men simultaneously, or at least 2 simultaneously, and then really enjoy it. So to me, that's like that's a pro.
Involved in increasingly violent and even
What do you mean violent? What are you talking about?
degrading acts. There's this whole genre.
Degrading? I mean, depends on the porn. There's like fetishes, so she can be a dom. It depends on what she likes. She should do what she likes, like in any job. Like, like what you do you enjoy what you do? No, so that's what you should do. Don't do it. Like, let's say you making this video, you'd really not enjoy it for some reason. So don't do it. Don't do it. We're not living in the pre-humanity era that we have to do what we don't like doing. Like, today, you can do whatever you want. Basically, the universe is flexible. You're a smart guy. You have degrees. You can do whatever you want. So she like, in porn, there's so many genres in porn. There's genres in porn where you're not touched, you don't do any sex. It's up to you. It's whatever she wants. She'll find whatever she likes, if she likes or not. But like I would say like in any field, very few become very successful in any field. Very few become Bill Gates and Elon Musk.
Genre of pornography called abuse porn, and it's what it sounds like. It's not stuff that is for the faint of heart.
It's whatever you like. If the chick likes it, that's it. If she hates it, that's it. Why are you making these faces?
Your ass roll. Oh, today was just so horrible though. Oh, you still got it done. Still got it done.
Okay, so she doesn't like it, then don't do it. Some chicks, that's what turns them on. Like there's two extreme chicks. One loves beating up men. That is what turns her on. The other chick loves getting beat up by men. That's what she loves. Right? Each should do like they shouldn't switch roles. They would have a terrible time. They should each do what they love. At the end of the day, it's like when I watch porn, I need everybody to really enjoy themselves. Except for the men. The men need to suffer.
But according to the Kinsey Institute, it's 40% of the pornography that's posted online fits the
Oh my god. Another day, another Biden voter. Okay, go vote for Biden. We know. You need to save humanity. Save like another savior to humanity faking his fainting.
this category. And the
Pearl crouching. Oh, oh, the girls are suffering. Porn is so terrible. We need to ban porn. That's the next thing he's going to say. Ban porn.
girls in this documentary were on the fast train into the belly of that beast.
That last part, I hate it.
And so all of that, it's a long way for me to introduce my guest today, whose name is Rachel Burnett.
Okay. She hates it. Like, switch jobs. Like, I hated so many of my jobs. What do you think? You're going to love every job? You don't have to stay there. You can keep looking. You can be, stay at home for a while, figure things out, keep looking for other opportunities. There's plenty of them, at least in America, and the rest of the world, pretty much not.
Bernard. She was one of the leads in that now almost 10-year-old documentary where she appeared under the pseudonym Ava Taylor. I just want to say, I love this channel. I love the fact that I can do deep dives.
Yeah, so you should continue. But if you hated it, then you should stop. Just like her. If she hates it, she should stop. Unless the money's good. But that means she likes it. It's like at the end of the day, we're all the same.
And interviews and explorations of topics that fascinate me here on YouTube. And thank you so much for your support along the way. If you want early access to my videos, go check out my Substack where I have a weekly newsletter, also my Patreon, where I post this stuff early and you have the ability to support the journalism that you love too. Otherwise, no worries. I'll see you here on Tuesday. Thanks so much.
You are wrong about everything. Comment. All right, let's get back. Oh, I'm cold. All right, fluid viscosity and shear stresses animation. Let's try that.
Consider a hypothetical experiment in which a material is placed between two very wide and large parallel plates. If a solid, such as steel, were placed between the two plates and loaded with the force P, as shown, the top plate would be displaced at some distance and the material will change its shape. As you can see the red point, it changed its initial location from point A to point B. If it deforms by the angle gamma, then this angle is called shearing strain, which is usually measured in...
This is GR's frame dragging. So Einstein says, basically, I would say this is what is causing Mercury's precession, according to Einstein, that he views space-time to be basically a solid.
in radian. We also need to note that, to resist the applied force, P, a shearing stress, would be developed at the plate material interface, and it is given by force applied per area. The effective area would be the upper plate area. It is well known that for elastic solids, such as steel, the small angular displacement, called the shearing strain, is proportional to the shearing stresses that is developed in the material. This is Hooke's law. Where G is modulus of rigidity, it is the ratio of shearing stress upon shearing strain. Now, what will happen? If this steel is replaced with water, and the force is applied to upper plate, keeping lower plate fixed. In this case, the water will of course deform with certain angle, and also shear stress will develop.
Good. They show that beta is an infinitesimal angle. And very good. They're showing the stress on what? That's the stress. Well, force is applied to the upper plate and it's moving to the right. Therefore, right, there is an opposite and equal. Well, not opposite and equal, but it's not equal. That's why the plate is moving. So, but there is a force to the left, and that is because of tau shearing stress. Perfect. And it causes deformation, a micro deformation in the water over a small period of time.
Develop, just like modulus of rigidity for solid, there is viscosity for fluid. Similar to modulus of rigidity, viscosity is the ratio of shear stress to strain rate. Strain rate is
Amazing. Yeah, it's a little bit different, but it's similar enough that I can reinterpret. I should be able to just reinterpret Einstein's stress tensor into my. It's a fluid stress tensor instead of Einstein's solid stress tensor into my fluid stress tensor. It's similar enough. You see the parallels. It's close enough. The only difference is that beta for fluids is infinitesimal in the analysis, whereas gamma for solids is a real angle. It's not infinitesimal. It's measurable. Beta is not measurable. It depends on delta t. So as dt goes to 0, delta b goes to 0. But the ratio between delta beta or d beta to dt, that ratio is maintained. And that ratio is the strain, or they call it the strain rate. Very good. They give everything a name. That's so good. Really a good channel. Finally.
the change in strain or deformation of a material.
It's so good to hear different people explain the same thing. It's really good. It's a really good idea. Just listen to the same thing. Once you know it and you really understand it, keep listening to different people saying the same thing. Then you're able to start saying, oh, this one I understand better. This one I like better. This one I feel is wrong. This one is more correct. Then you can have your own opinion. That's when the fun begins.
With respect to time. As time passes, fluid get deforms. But later in this video,
It's not actually time. It's an infinitesimal time. It's not as time passes. It's as the time that passes tends to 0. It's not it's not really time. It's an infinitesimal time.
you will see that the rate of deformation of a fluid.
Like if you would think, oh, time passes, so it's like, no, that's not how you do this analysis. Time doesn't pass. It's an instant. At the end of the day, we're talking about an instant. Time doesn't pass. But the ratio of the change in the angle to the change in time, as these changes tend to 0, the ratio is of a certain amount. And it depends on, if everything all else stays the same, it depends, let's say, on the force, on P. So you apply P, and instantaneously you check the change in the angle over the change in time. How much time passed? Like an infinitesimal amount of time. Let's say a microsecond passed. And what's the angle that changed? Very, very, very tiny numbers. The tinier, that's actually the more accurate your measurement is. And then you're asking, okay, as I'm increasing the force over the same amount of time, I'm getting a bigger angle. And as I'm increasing the force over the area, right, P over A, so the shearing stress rises. So as tau rises, this angle should rise linearly because mu should be a constant for the same fluid. That's our assumption. That this is it's a linear system. Very nice.
Element is equivalent to the velocity gradient. So you can write viscosity as the ratio of shear stress upon velocity.
So what was it before? Very good. The change in the angle over time.
Element is equivalent to the velocity gradient. So you can.
Yeah, they skipped over a few steps. So it's not really, you see, here is my opinion. So if I would have watched this video first, I would have asked, how did they get to du dy? Like they just skipped from an angle d beta to du dy. How? So yeah, there is a derivation. You have to do. This is an approximation, but it's fine because we're talking about an infinitesimal angle. So for an infinitesimal angle, yeah, d beta is du dy. It's absolutely correct. But when we do the geometry, we're doing an approximation because the tangent of d beta is the ratio du dy. But under a small angle, the cosine is 1 and the sine is the angle. So d beta is du dy for an infinitesimal angle. It's absolutely correct. At that point, it's not an approximation. So in terms of calculus, it's not an approximation. It's correct, and it should give you perfect answers every time.
Can write.
Of course, we're assuming mu is a constant. That needs to be tested. That has to be empirically verified.
Viscosity as the ratio of shear stress upon velocity gradient. Now let us get deeper in it. Remember, water always sticks to the surface.
Very good. They put whatever they derived, they put small at the bottom. Like a lot of videos, they just throw it to the garbage and they don't show you whatever was derived. I would also always show so that the person doesn't need to look back. I would make tinier and tinier, but leave it on the screen so that the person I can always reference whatever I need to reference. I don't have to scroll back.
So water particles at top and bottom layer sticks and when constant force is applied, the top layer of fluid moves with the same velocity of plate. But bottom layer have zero velocity. These particles sticking to surface is because of the no slip condition. The bottom layer fluid particles.
She's saying things that are difficult to understand. This is the no motion principle or assumption. There's a bunch of assumptions. It's difficult to understand what she's saying. They should write out these conditions. Anyway, everything she's saying should precede the derivation of the equation. So there's no point in explaining now. It's too late. You already derived the equation based on everything you're now basically explaining that you're assuming. So first you set up your assumptions. Only then can you start doing the derivation. There's no point in explaining the assumptions now, I don't think.
Tries to slow down adjacent layer and so on, and that's why velocity changes along the distance between two plates when upper plate is moved. The velocity is changing with respect to distance between plate, so we call it velocity gradient. In steady laminar flow, the fluid velocity between the plates varies linearly between 0 and maximum.
Yeah, that was the assumption. It's too late to explain this now, I think. isn't it? Or maybe you're saying du dy is not linear, and like until now you didn't assume it's linear, and now you're going to tell us, well, let's make the assumption. Now you're assuming linear. Does it have to be linear? I don't know. It looks like it has to be linear. Unless we're assuming turbulence. As long as we're assuming laminar, then I think we can, it's not an assumption that it's linear, but still you need to verify it empirically.
Velocity v. With this linear relation, we can easily obtain velocity at any location by using similar triangle relation. Let's find velocity at any location y, if u is the unknown velocity then, by similar triangle relation. Now this is the velocity profile, which is a function of distance between plates, and again by taking their derivative you can easily obtain the velocity gradient. Now we need
Du dy is just the velocity at the top over the distance between the plates. Yeah.
to get the relation between the angle of deformation and the velocity gradient. During a differential time interval dt, the size of fluid particle.
Very good. She calls it a differential time. That's interesting. A differential time. That's good. I would say an infinitesimal time, but fine.
Along a vertical line
Differential doesn't imply that it's infinitesimal.
rotate through a differential angle beta, while the upper plate moves.
But it's good. It's good that they're stressing that these are differential or infinitesimal values. Very good.
Differential distance.
Good habit, and it's good to be correct than wrong.
dA equals vdt, as velocity is distance.
Very good. What is dA? VDT, because A might be confusing. It sounds like a acceleration, but really it means length. Okay, she's just defining A or dA. Okay, a little bit confusing to use A. I would use, L she already used for length. I would even use X.
Distance travel upon time taken. Then solving these geometry.
Wait, now she's doing the derivation? That's not a good idea. Okay, so d beta is basically tangent of beta. She doesn't explain why. It's the opposite. It's actually dA over L is equal to the tangent of beta, which is basically, you can simplify it to, that's not the point. You don't want to go from d beta to tangent. No, this is wrong. D beta is not the tangent of beta, it's the tangent of d beta. This is wrong. Did anybody catch it? 455. Nobody caught it. Translate to English. What an idiot. No one caught this. Parabolic. Your professor didn't prove it? That's terrible. This is completely terrible. Anyway, d beta is not approximately tangent of beta. There is no angle beta. Angle beta is 0. So this is 455. So d beta is equal to approximately tangent beta wrong, rather d beta. So it's tangent. Let's just put parentheses. Tan d beta. All right, whatever. We've seen these derivations.
Look, we proved it.
The ratio of d beta to dt. Okay, let's see the proof. So d beta is tangent of d beta. So the tangent is dA over L. dA is vdt. And we already showed that v to L is du dy. So du dy dt. So we divide both sides by dt. So d beta dt is du dy. All right, what are you going to do with that? But what does that mean? That means the ratio of the change in angle to the change in time is the change in velocity as you go up. Right? This change, right? This change in u, or du dy, right? This change du dy is this little angle. And this little angle is this little angle. But that's not true. It's not that that's not the point. It's the ratio of this angle to dt. But we lose this information because of the approximation. This is already the result of an approximation. So, hold on. Right? du dy, right? du dy, these are infinitesimal amounts. They're insignificant. There are two zeros. But the ratio of these two zeros is this to this is equal to the tangent of this tiny angle, which is the tangent of this tiny angle. This is not du. This is du dt. That's the problem. This is du dt to dy. Okay, now I got it. So du dt is this distance. Du is not a distance. This is du dt. Du dt, which is double infinitesimal. So it's even more insignificant. So du dt to dy, nevertheless, it is the tangent of this angle. And the tangent of this angle for a tiny angle is the angle, which is d beta. So it's good. So we have a zero amount is equal to a zero amount. divide both sides by dt, a zero amount, and you get ratios, which is what we're getting here. So the rate of change of the angle, that's the answer. The rate of change of the angle, which is a real amount, that's not infinitesimal. The angle itself is infinitesimal, but the rate of change over time of the angle, that's a real number. The rate of change of the angle is the change, it's a sort of rate, is the change over length, over these distances, or the way this distance changes over the ratio of this distance to this distance. Right? The bigger this distance to this distance, the faster this angle would change instantaneously. Something like that.
That the rate of deformation of a fluid element is equivalent to the velocity gradient. Further, it can be verified experimentally that for most fluids, the rate of deformation is directly proportional to the shear stress. And so is velocity gradient. Then
So basically, which is proportional to the force, or equivalent to the force, or yeah, linearly proportional to the force applied. So as you apply more force, you can measure a greater rate of deformation. You apply greater force, greater rate of deformation. Fantastic. What did she say about this?
by the linear relationship of shear stress to the shear stress. And so is velocity gradient. Then by the linear relationship of shear stress, where the constant of proportionality mu is.
And it's equal to, if it's linearly proportional, I think this means linearly proportional. I think this is what they usually mean by this. So linear proportion, by definition, means equal to a coefficient by. So the coefficient is a linear coefficient now, or a constant, that's mu for each fluid. And that's the viscosity coefficient.
Is called the coefficient of viscosity, or the dynamic or absolute viscosity of the fluid. As you can see, how it relates with the shear stress, deformation rate, or velocity gradient. If you look this figure properly, viscosity is actually a coefficient in a stress-strain relationship. You can verify taking slope. Its ratio appears same everywhere. Shear stress versus the rate of deformation is a straight line whose slope is the viscosity of the fluid, as shown. Fluids for which the rate of deformation is linearly proportional to the shear stress.
They should show an experiment. Like, show me an actual experiment where this was conducted. I'm curious. Like all these things, if like, show us experiments.
Are called Newtonian fluids. This is the plot of viscosity of water at 20 degrees Celsius. Most common fluids such as water, air, gasoline, and oils are Newtonian fluids. Remember, for water or Newtonian fluid, viscosity is always linear, no matter what. But for solids such as steel.
What?
Remember, for water or Newtonian fluid, viscosity is always linear, no matter what.
Well, by definition, I wouldn't say for water no matter what. That's ridiculous. Obviously, water is going to start losing its linear form, like laminar flow. Obviously, you're going to get an air. Obviously, I mean, all these things, you're going to get turbulences.
But for solids such as steel, modulus of rigidity is not linear forever. There comes a
The same goes for Newtonian fluids. I mean, this is just an approximation under certain conditions where they are linear. Sometimes they are linear, sometimes they become turbulent. And the same for solids. They become, this is the elastic range, this is the plastic range. Right? Elastic, and even the elastic, over time, it becomes plastic. It's like very, these are approximations, obviously.
point where Hooke's law is not applied.
Oh, it's called Hooke's law. Very nice.
Please subscribe for more animation. For now, enjoy reading. And bye.
For now, enjoy reading. Okay. More YouTube. Mm. Viscosity and shear stress. 1. Fluid mechanics. Steven strangles debate live now. Steven strangles people. What? What is that? Who is that? What's going on? 1,000,000? Oh my god, so many subs. Real physics talk. This guy, Unziker, I never understand him. He doesn't have, like me, I have a theory of everything, always. In every field, I either have a theory of everything or I strive towards a theory of everything. This guy's like always talking about this minutia, that minutia, and like, when are you going to present your theory of everything? It's like everything is always, let's discuss this detail, that detail. Everybody's wrong about this detail, that detail. It's like, you're wasting my time. Let's see this guy. What?
Hello, everybody. This is very exciting because SpaceX are going to try and launch Starship for the 5th time. And this time, depending on how things go with the booster, they might actually try and catch it with the tower arms, which will be quite the sight to see. So,
This was unbelievable. This was unbelievable.
needless to say, I'm very excited. Let's see what happens. I'll tell you what. Looks like a very pretty day for a launch. Very pretty. Super looking forward to this. I hope it goes. That's always the risk with rockets. It might not
In America, we say it's a beautiful day. We don't say it's a pretty day.
actually take off at all, but especially with experimental ones. But yeah, this is, if it does go, this is going to be stunning. So rather unsurprisingly, they are not going to recover the Starship. That's going to be landing off the coast, or landing sort of,
What's the point of having such an expensive mic? That's such an inconvenience. You have to lean towards it. Such an inconvenience. I mean, you're wearing a headset. Might as well have a mic in the headset, like me. Like you probably spent hundreds of dollars on this just because of. I mean, it's such an expensive setup. Physically, it's expensive. Not that, I mean, internally, the electronics is, it's very standard, but the mechanics is so expensive and such an inconvenience and takes up space on your desk. How can you live like this? And you're already wearing a headset. Just put a mic here next to your cheek and you're done. I don't understand people. I don't understand them.
soft splashdown in the ocean off the coast of Australia. So it's going to go a good sort of,
Oh,
halfway
it's off the coast of Australia. Yeah, like Indian Ocean.
around the world, which is, pretty cool. And that
I
level
wonder
of
if they had to get permission from anybody because it's like ocean. Does anybody own the ocean?
distance covered,
I
you're
wouldn't be
basically
surprised that the FAA forced them to get permission,
in orbit. In fact, I think they're just going to adjust their trajectory a bit so that
even though the FAA has nothing to do with Australia or the Indian Ocean. But the FAA demands, and whatever it demands, you have to fulfill.
it isn't orbit, but it will be an orbital level of energy that is transferred into the Starship. The booster, however, is going to do a boost back, and we hope, possibly, if everything is looking good, get caught by the tower. That's the bit that to be honest, the whole thing, last time the re-entry was stunning. I'll be fascinated to see if they managed to fix the burn-through problems they were having on those front flaps, and I think all the flaps took a bit of a beating, but hopefully we'll get great footage of that, and it re-entering, we'll actually be able to see have they made some progress with that or not. So they're running a little bit late in the window, but they just said that the reason for that is because range issues, not a technical reason. They have a built-in hold at T-minus 40 seconds, where they can then sort of wait if they need to, if there's range issues. At the moment, like I said, no technical problems, and the weather is 100% yay. So
Look at the second tower, but it's not finished.
that's great, because weather is always a big iffy thing when it comes to rockets.
I heard it's going to take them another year to finish the second tower. I don't know.
Especially when they're in their sort of test and early adoption phase, where
How are they going to attempt to catch the second stage if it's going to be so soon after the first stage? So naturally, I mean, ultimately, there's going to be a big difference because the second stage should be in orbit. It's supposed to deliver something. So it should be going into a complete orbit, deliver its payload, and then come back. So by that time, they would have removed the first stage from the tower. But if they do a suborbital second stage, I don't think they're going to have enough time to remove the first stage. But I don't know.
The sort of envelope that they're known to be able to fly in is quite narrow. Like, for example, Falcon 9 these days seems to launch in weather that it definitely wouldn't have launched in, in the first year or two of its active service.
So this is the trajectory. I never saw this trajectory. So it's very difficult to understand. This is Texas. It's launching. This is the Yucatan Gulf or something. This is where the dinosaur killer asteroid landed and created this gulf. This gulf is the result, I think, of the asteroid, the dinosaur killer asteroid.
This. Right. Anyway, propellant is loading. We're about 2/3 of the way through that now, and there's 12 minutes, 40 seconds to go. So, it's exciting. We're getting there.
Mechazilla.
I just hope there's nothing wrong with the range. I hate it when things stray into the range. I mean, I understand how and why it happens, human error and all of that, but still, it's frustrating.
I think they had half an hour between between landing the booster and re-entering with Starship. So, and that's not even a full one orbit. So if they do a full one orbit, that's probably an hour, which should be enough to remove the booster from the tower and prepare to catch Starship, the second stage.
For me, as an amateur rocket watcher. So yeah, if there's anything wrong with the booster or they just don't feel like doing it today, they're going to divert it into a soft splashdown in the Gulf of Mexico. So that's the backup plan, because everything on the booster, there's like a bunch of automated checks that the booster will do itself, and then the actual flight director has to sort of press a button that says, yeah, okay, come on then, let's give it a go. Which, if you think about it, there's a lot.
I need to send an email. Wonderful. Wonderful. What else is new? Jesus Christ. Oh my God. I'd rather not read the news. Okay, let me just check an email. I gotta do something. Tira la 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 la. Let me get his email. Copy. What is going on? Got it. Okay. So let me try and find the documents that are missing. There's one document. Let me see if I can get the other one. Let me see the other one. I don't see it. I don't see it. One document, the other one I don't have. Let me go find the other document. Where is the other document? Let me see. I don't see the other document. So let me check one, maybe here. There it is. Got you. Let me check if it's now available. Got it. Okay, so he said oh, he wants my documents too. Oh my God, my documents. Let me try and find them. Find them and destroy them. Collections. Where is my documents? Where's my favorites? Why can't I? From Gmail, I don't have access to favorites? That's terrible. Oh, there's favorites. And favorites, there it is. Okay, we're good to go. So I think that's all he needed, right? He asked for, yeah, that's everybody. You got it. We're good to go. Okay. What else? So that's done. I don't care. I don't care. I don't care. Don't care. What is this? Let me share this. Where is this? I didn't have a chance to look. Let me look now. Is it going to show me? Yes. There you go. So, did I share it? Hopefully. I don't care, don't care, don't care. Update. That's good. I don't care so much. Don't care. What? I doubt it. Yeah, it's fake. Let's report this as report spam. Unsubscribe. Yes. Okay. I don't care. Don't care. Don't care. What's this? What is this? I don't know what's going on here. Why am I getting this? Is this again? No, I already shared these, so that's fine. So we're fine. This is fine. I don't care. Oh my god, I need to remove things once I share them. Num 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 num. Yeah, I don't care. I don't care. I don't care. I don't care. Don't care. Don't care. Don't care. Okay, I'm not gonna waste everybody's time sifting emails. Did I finish my coffee? Yep, looks finished to me. Okay.
A lot riding on that because if they try to do a catch and it goes wrong, they might not be able to launch again.
Okay, I don't care. I mean, I care, but I gotta do stuff. She defends Israel, now Egypt wants her dead. What else is new? Real physics. Oh my god, this guy's so boring. Unlocking the secret of microRNA. The Dubai they don't show you.
What up, y'all? This is the Dubai they don't show you. With Dubai being one of the most popular destinations in the world, having massive skyscrapers and a luxury lifestyle, at one point it was a small fishing village that many people overlooked. And what many people don't see is Old Dubai, which is the original Dubai before all the large, lavish buildings. This is where you can find one of Dubai's oldest neighborhoods.
I wouldn't say this is the original. I would just say I don't know why they're not converting this into the skyscrapers. I mean, real estate in Dubai is very expensive. So why are these small buildings even there? Why aren't they converted into skyscrapers? That's weird. And I'm worried. I'm worried that the zoning laws prohibit it. The king probably said, no, we have to keep the old. We need to keep the old. And the owners really want to build. They really want to build. No, 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 no. We have to preserve. We have to preserve. And yeah, basically, that's life. That's basically that's the problem of the West. The West needs to preserve. We need to preserve the forests and preserve the poop. We have to preserve the sewage. Everything needs to be preserved. Don't change anything. No, let the asteroid destroy us. Don't change anything. The asteroid is about to hit us. You're not allowed to change. You can't change the asteroid. It must destroy us because we have to preserve. Don't change the asteroid trajectory. Yeah, don't change it. Don't change it. Yeah, we're doomed.
Which is called Dira. You'll find hidden gems like the spice souk,
Disgusting. Absolutely disgusting.
the gold souk, which is the cheapest place in the world to buy gold. And this is where you can find the heaviest gold ring in the world, which weighs about 133 pounds and is valued at $3 million. You'll also find the famous Dubai Creek, which was the most important part of Dubai's early beginnings. Visiting old Dubai showed you the humble beginnings of an old fishing.
Absolutely disgusting. Absolutely disgusting. Why would you want to preserve such? So why did you convert Dubai from a desert into a city? You should preserve the desert. Just preserve the desert. You shouldn't touch the desert. Preserve it. Looks fun and authentic. No, it doesn't. It looks like shit. You like the old Dubai better. Yeah, this is why we're doomed. So the oldest Dubai is a desert. Go live in the desert. An actual place where real people live. Real people. Real. This is much more appealing. Oh, much more appealing. Go live in old Dubai. Let's see you go live in old Dubai. Traffic around the clock. You can't move. Traffic around the clock. No parking. You can't have a car. You live in an old, dilapidated apartment if you can find one. Yeah, go live there, genius. Don't live in the skies. But of course, when they go visit, they go to the lavish parts. The Dubai they don't show you is where you will find locals having kark with Indians and arguing over the price. Yeah, because they're poor. Sadly, I never knew, and all the comments are positive. I prefer the culture in old Dubai. The old. Where do you live? I live in the new. Oh, okay. Have you ever visited the old? Yeah, once. That was enough. I got stuck in traffic for a day. Yeah, that was enough. The old is better. The old is real. This is my kind of place. It's my kind of place. I love the old Dubai. It's definitely my vibe. Old, and my grandma's old. Just one day, stopper on my way to Hong Kong, and as impressive as the new stuff was, I much more enjoyed the old Dubai. The old, much better the old. I love the video. Love the village. Oh, I love the old Dubai. Yeah, old Dubai's gold Dubai. Oh yeah, the old. I love how all parts of Dubai are clean. Yeah, the old is not so clean. Me, who just came back from Dubai and watched this, crying. Why are you crying? I would love to check. Anyway, even old Dubai looks fascinating. No, it doesn't. It looks disgusting. Thanks for your lovely, rad, awesome, cool, gorgeous, exquisite, beautiful, and marvelous tour. It's disgusting. A camel. Ugh, disgusting. Now that's what I want to see when I visit old culture and tradition. Of course. Where do you live? Oh, I live in the new. Okay, that's good. I miss Dubai. I hope I could visit. I'm not even going to comment. Fluid dynamics. Electric field due to an infinite surface. How SpaceX landed. Let's listen to this.
Hello, it's Scott Manley here. Today I woke up at 4 a.m. because SpaceX were scheduled to perform their most ambitious Starship Super Heavy launch yet. I mean, honestly, every single one of them has been more ambitious than the last, but this one seemed particularly audacious because they were going to perform something which had never been attempted before. Sure, SpaceX had been able to land hundreds of boosters on drone ships, but today they were hoping to be able to pluck it out of the air using a launch tower. Mechazilla was going to reach out with open arms and carefully grab that booster by two very small pins on the side. Were they going to be able to do that? Well, that's why I was up at 4 a.m. Did they do that? Well, by now I think a lot of you know the answer. Yes, they did. They succeeded in both of their goals, not only landing the Super Heavy booster on the tower, they also successfully descended a Starship through the atmosphere with pinpoint accuracy and landed that too. And frankly, this achievement is a marvelous testimony to the power of engineering and human ingenuity. We all knew that this was technically possible, but we were.
This is what? How did he say it?
Frankly, this achievement is a marvelous testimony to the power of engineering and.
This is a testimony to Elon Musk. No one gives him credit. It's like the haters hate him and would never give him credit for any accomplishment. But even people who love Elon Musk don't give him enough credit. I mean, this is Elon Musk. This is this is what it looks like when you painstakingly do something like a genius. No one has done this. This is one person doing this.
And human ingenuity. We all knew that this was technically possible, but we weren't sure it would actually happen because there was so many things that could go wrong, so many small factors in the engineering, the physics, the things that happen when you try to take something that.
This is Elon Musk driving his company insane performance. No one would even think in this direction. Where he's going, no one is even thinking to go.
That works on paper and actualize it into reality. I myself demonstrated this in Kerbal Space Program many years ago, but I didn't have to worry about budgets, risk to human life, or government paperwork. I also had the ability to play the video backwards. So this was going to be the 5th flight of the combined Starship Super Heavy stack.
Oh, it was the video backwards. So even in a video game, he couldn't get it, and Elon Musk did it, basically on the first try.
To summarize how we got here, the first flight got off to a rocky start, and I mean that literally when a rock tornado cast debris all over the area. A number of engines failed, there was a fire in the rear, they lost control of the booster, it eventually spun out of control. Neither of the things separated, the flight termination system fired, but it didn't actually destroy the rocket until a minute or so later. Flight 2 solved the rock tornado problem by having a giant showerhead pointing upwards, a water deluge system that protected the surface. And moreover, it seemed to help protect all the engines, and we had 100% success, at least early on in the flight. The backflip stage separation procedure was replaced by a more conventional hot staging system, which required adding a hot staging shield on top of the main booster. And this ended up delivering a successful and spectacular stage separation sequence, which moments later got even more spectacular when the booster exploded. Starship would continue downrange, but it ran out of oxygen and they terminated the flight. Flight 3 would push the envelope out even further. After hot staging, both stages would then go on to complete the burns they had intended. With Starship heading off across the oceans and the booster coming back into the Gulf of Mexico, it descended straight down through the atmosphere and then was lost. Starship would perform a number of tests on orbit, but it lost attitude control, and without that, it was destroyed on re-entry. For Flight 4, the big change was that they were now going to jettison the hot staging ring because it had added extra mass to the booster and they didn't really have the margins to get it back safely to a soft landing. So after the stage separation and boost back, they dropped the hot staging ring, which would fall.
The next step is to keep the hot staging ring. That's going to be a challenge.
On its own into the Gulf, whereas the booster, it continued down and under good control and demonstrated a descent through the clouds at multiple times the speed of sound before lighting up all the engines, decelerating really, really quickly and slowing itself down.
Let me check what's going on with my friend Amber. Hi. 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 Fligagigu, Andrew. Hi. Actually, I don't want to waste time with Andrew. He's a big time waster. And anything else interesting? Divine. I don't remember any of these people. Totoro, Choking. How's Choking? She was nice. Hi. Okay, let's see what's up with Amber. Wait, what just happened? I need to remove myself from all these groups that I can't join anymore. Hey. Tina, hi. Tira la 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 la.
to a soft landing in the Gulf of Mexico. And the reason we have these images is because there was a boy there that had a camera. More importantly, this demonstrated the precision they needed to move on to the next step in their test plan. Starship's descent was even more spectacular because it began to disintegrate. We started to see holes being burned through those control fins, but it was miraculous that despite the damage that it was sustaining, it continued. It managed to maintain control all through the descent and land.
Wow, it basically was detached. How did it survive?
Safely in the ocean. So for Flight 5, Starship's task would be to land precisely.
Whoa, basically the flap was completely loose.
Where it was expected. Now, I had been concerned that the launch might be delayed. They had pushed it to 25 minutes into their 30-minute launch window, but it went off on schedule, and the early part of the flight has become well understood now. It took off, it didn't throw rocks everywhere anymore, and it ascended through Max Q in beautiful sunrise, by the way. This low sun actually made for probably the most photogenic launch yet. Like, not only was it early morning, nice, beautiful, deep red colors from the sun lying low in the sky.
So this is yesterday.
It also meant that the sky was a bit darker and the plume was much easier to pick out. And also, as it got higher and we began to look down, you could see a dark shadow being cast across the Earth by the low flying,
Oh, that shadow? What is that shadow?
The low sun and the long vapor trail. So that portion of the flight is great. It's well rehearsed. The real action starts at staging, where you have to...
What's causing this line? That's weird.
To do a lot of work with the rockets planning to shut down engines, start up other...
Oh, because of the sunrise. So the sun shining, so this is its own shadow. It's so long because the shallow angle of the sun. Okay.
Engines, and then restart a bunch of engines, and that's the time where we've seen things go wrong before. But again, everything seemed to work fine. In fact, one of the things I really like...
It didn't change, so that's not the cause.
About this particular sequence on this flight was that, well, first of all, we got to see it from the ground. That's great. But the onboard camera from Starship was able to pick out the booster in the distance. So as the Starship maneuvers to its new...
The booster... From here, you could see the booster? Where?
Attitude. You can see that bright light in the middle there. That is the booster firing. So I'm just going to zoom in here. So that's the Starship on the left. The booster is on the right. And yeah, that white light that is seen on the Starship camera is the booster firing its engine. By the way, on the booster side, see that pin that sticks out? That is what is going to get caught by the tower. That's
the pin that's going to, it's going to actually land on Mechazilla. Yeah. And it lands on a soft chain. Would you say it's a soft chain or like a soft thing that like a mobile strip, like a Moby strip?
Into the capture mechanism. So it performs most of the boost back on 13 engines, and then as it gets towards the end, it shuts down 10 of those engines. That's what that pulse was, leaving 3 engines to do the final, like, precise correction for entry. Then it shuts down those 3 engines. And again, you can see the puffs on the left side as it does that, and then it purges the engines. Okay, so now the booster is on the way home. This is a view from Starship showing one of the new cameras showing the backside of one of the forward fins. The booster was lobbed onto a trajectory, which is bringing it back just off the coast of Boca Chica. It looks like it maxed out at 96 kilometers, so technically not over the Kármán line according to Blue Origin, but over the Kármán line according to Virgin Galactic. So you can decide whether it went to space or not. But point is, this booster is big, it's heavy, it has propellant on board, and it has been put on a trajectory that if it failed now, it will land just off the coast. And for it to actually get to the landing site, it's going to have to perform a glide using those grid fins to steer itself. Now, this sequence here...
Not just the grid fins, also the shimmies, I think they're called.
If you look very carefully, you can see the hot staging ring has been detached, and it's now performing small maneuvers with its cold gas thrusters. So those aren't rocketing.
I didn't see the hot staging ring getting detached.
So you can see the hot staging ring has been detached, and it's now performing small maneuvers. It will land just off the coast. The booster is big, it's heavy, it has propellant on board, and it has been put on a trajectory that if it failed now, it will land just off the coast. And for it to actually get to the landing site, it's going to have to perform a glide using those grid fins to steer itself. Now, this sequence here, if you look very carefully, you can see the hot staging ring has been detached, and it's now performing small maneuvers with its cold gas thrusters. So those aren't rocketing. I mean, they are rocket engines, but they're not burning anything. They're just releasing gas through nozzles, and that provides just the small amount of thrust needed to trim its trajectory to be in exactly the right precision. That hot staging ring, of course, is discarded. It's just been a smash.
That's the hot staging ring. Wow.
Water at high speeds. So anyway, yeah, the booster has to autonomously navigate itself to the target, and if at any point it fails, it should just land in the water harm.
Yeah. They could probably salvage it. No, but it got smashed up when it landed at high speed in the ocean. It's really dangerous. I mean, this is right. Is it off the coast? Yeah, it's very close to where it took off from. It's very close to Boca Chica, so. But, no one is supposed to be there, so fine. Wait, is anybody watching? Nobody's watching. Oh. The Predator. Hot women having sex with guys with big dicks. This must be banned. Yeah. Basically, The Predator. La 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 la.
harmlessly. But they also had to explicitly send a command to the booster. They would do a checkout of the tower, they would do a checkout of the systems. If everybody gave the thumbs up, they would send the enable command, and the booster would say, right, that's my mission. So you'll notice over the last few seconds, it has aligned itself to the entry attitude. The other thing to notice is those puffs of gas that we saw that were initially coming out a long way, those are now getting pulled along by the atmosphere. There's not enough atmosphere to provide drag to the booster, but it's picking up the gas that it's emitting and sucking it backwards. We're now at 100,000 feet, and the atmosphere is thick enough to actually hold balloons up. It's moving at Mach 4, and the speed is starting to decrease as the booster gets enough drag. This is much faster than a Falcon 9.
It's turning red. Did it turn red? It looks. Is this turning red? This is supposed to absorb most of the energy during re-entry.
Thick enough to actually hold balloons up. It's moving at Mach 4, and the speed is starting to decrease as the booster gets enough drag. This is much faster than a Falcon 9 booster descends. And now we switch to a different camera on the ground.
A Falcon 9 booster actually uses its engines to slow down during re-entry.
Leaving a trail, but look at the bottom of the booster. It is hot.
Yeah, that's incredible. It's glowing red hot. Wow. I think in the next flight, all the puffs that we saw, they're going to release from the bottom to cool these engines. This is destroying the engines, I would think.
And you might think, well, the rocket engines, of course they're hot, but no, they've been shut down for a few minutes. If you look very carefully, it's actually the shield around those engines that's hot. That is the result of atmospheric heating inside the engine skirt. And so now with it plummeting towards the ground, it's time to slow down. It lights up 13 of those engines, performs a rapid deceleration to make sure that it's not going to hit the ground. And then for the fine control, it switches back to 3 engines. Now, as it gets really close, it makes those last minute corrections, bringing it in close to the tower between the giant's chopsticks, and Mechzilla closes its arms around the booster.
I wish we had a video of those seconds. I mean, it's good to have a video from a ground or whatever from the drone, but also I'd like to have more angles to see, because I felt like it's about to smash into the tower. I was sure it's going to smash into the tower from my angle.
Carefully putting itself under those pins and holding the rocket for a successful catch. And of course the crowd goes wild, just like at a baseball game when the star batter is caught out. But let's rewind and I'll show you a couple of things that I saw here. Firstly, you might have noticed some debris getting shed. That is from the bottom of one of the chimes. You can actually see that a section has been cut out. There's at least one other camera angle that they showed later, which you can sort of see it on the right there as it's descending through the grayed out area at the bottom, the framework. Another thing that's really cool to see is the way that it is actively maneuvering.
What happened?
During the final portions of flight. And a lot of people said, oh my god, it looks really wobbly, I can't believe they caught it. But actually, if you look at what it's doing, this is a planned maneuver, and it's a maneuver that's planned with safety in mind. It is actually coming straight down so that if it fails, it is going to miss the tower. It's just going to land and you explode and not damage the tower. It's only once they are 100% sure.
Oh, finally we see other angles
that make that translation in towards the tower and then slow itself down. So it basically makes the sidestep at the last minute. If it wasn't sure it was able to do that, it would land somewhere less likely to the tower. It's going to miss the tower. What it's doing, this is a planned maneuver, and it's a maneuver that's planned with safety in mind. It is actually coming straight down so that if it fails, it is going to miss the tower. It's just going to land and you explode and not damage the tower. It's only once they are 100% sure does it make that translation in towards the tower and then slow itself down. So it basically makes the sidestep at the last minute. If it wasn't sure it was able to do that, does it straight down so that if it fails, it is going to miss the tower. It's just going to land and you explode and not damage the tower. It's only once they are 100%. Oh my god, it looks really wobbly. I can't believe they caught it. But actually, if you look at what it's doing, this is a planned maneuver, and it's a maneuver that's planned with safety in mind. It is actually coming straight down so that if it fails, it is going to miss the tower. It's just going to land and you explode and not damage the tower. It's only once they are 100% sure does it make that translation in towards the tower and then slow itself down. So basically makes the sidestep at the last minute. If it wasn't sure it was able to do that, it would land somewhere less likely to damage things. And yes, they did actually overlay Mechzilla doing a moonwalk. Finally, they included this angle, which is probably the best of the actual capture. So you can actually see the pins coming down towards those shock absorbing rails. So those are going to absorb any stress, and then they lower down into position and lock the booster. See, one of the big engineering problems with landing rockets is that as they land, you get a lot of forces placed throughout the vehicle. By putting those forces at the top and by incorporating the shock absorbers into the tower, they are saving a lot of weight in theory by doing this. And we knew that was the gain that they were making. We didn't know whether it would be possible, and now we're wondering, will it be possible to do this again? How many times, how repeatable will this process be?
Yeah, they're saving a lot of weight by investing more and more into the tower. The stiffer, the stronger the tower is, the lighter the booster can be in the second stage too. Yeah, it's very smart.
You can also see this vent on the side that's venting methane. And you see how it's burning up the top, and because of the airflow, the flame is trying to run downwards, but the airflow is pushing it up. And then around about here, it catches at the bottom, and a flame front runs up. This is just them purging various parts of the fuel system because they need to make sure that they're not carrying that on board, that it doesn't build up and become something that could potentially build up and explode. So yeah, that's great. They caught the booster, and of course there'll be a whole bunch of processes involved in saving the booster, recovering.
Good. There's so many angles, so many cameras that we didn't get to see. Very good.
The booster, putting the booster somewhere safe. But for now, I want to switch over and look at see what happened to Starship. So it ascended onto a suborbital trajectory. Although it was,
he gives good rundowns, good reviews, good analysis.
Moving at orbital speeds, it was not going to make a complete revolution. It absolutely had the performance to go into space if it wanted to. But anyway,
he doesn't even monetize his channel. Like, he works for Apple. He's actually an engineer.
Yeah, this would carry it over Africa. It would reach a maximum altitude of about 212 kilometers before beginning
And
to.
he's originally he was studying. He was a DJ. This is a DJ turned into an engineer on his own. This is incredible. This is the power of high IQ. You can do whatever you want.
To descend back down. And we knew that it didn't have a perfect heat shield. First of all, we could see a number of tiles were damaged, like look at the one on the front of that wing there. But also, they had replaced.
Where? Oh, these. Yeah, this is missing. And over here and over here. So a bunch of them are missing. But it has a backup layer. Single-use backup layer.
This number of tiles with test hardware, and they'd removed a couple of tiles in some places to see how the vehicle would handle it. But we also know there had been a redesign of the heat shield in a number of ways.
You saw how the what do you call this? The flap was pulled in. Did you see that? So now it's basically, I don't know if it's fully extended. It looks like it's fully extended. Yeah, this is full extension. So for takeoff, it's fully extended.
Yeah, this would carry it over Africa. It would reach a maximum altitude of about 212 kilometers before beginning to descend back down. And we knew that it didn't have a perfect heat shield. First of all, we could see a number of tiles were damaged, like look at the one on the front of that wing there. But also, they had replaced a number of tiles with test hardware, and they'd removed.
Now it's being pulled in. I don't know if it's being pulled all the way in, but it's a good angle to create aerodynamic stability.
The tiles in some places to see how the vehicle would handle it. But we also know there had been a redesign of the heat shield in a number of ways, and there was now like an ablative layer, I believe, was underneath this. So if there were tiles missing.
What do you mean I believe? Of course. They said so. That's what they said.
You would get some more thermal protection. And what I also like, by the way, is you can actually see reflections of the clouds in the polished stainless steel tanks. Now, again, on re-entry, you have to understand that in the upper atmosphere, the atmosphere is very thin, so you might get temperatures that are the highest because you're moving fastest. But until you descend into thicker atmosphere, the amount of heat will not reach a peak until you're like lower in the atmosphere. But that peak heating is not the same time as you get to peak drag, where the atmospheric drag is when the atmosphere is thickest, and at that point you may have slowed down a lot, but because the atmosphere is so much thicker, like it's a more different dynamical problem. So the Starship has to cross through all of these regimes. And all the time while doing this, it has to maintain the correct attitude with the the raw, naked stainless steel facing away from the brunt, the main heating from re-entry. You can actually see little pulses every now and then as it's firing RCS thrusters in this part of the flight, but eventually it gets deeper into the atmosphere and it begins to take.
Oh, these are RCS firing. Okay, I was wondering what the heck are these pulses?
Active control with the fins. You can actually see that rear fin is slowly adjusting itself. It's not just using that to maintain attitude. The attitude itself of the spacecraft has to be controlled so that the lift that the body generates will control it and carry it down to the target site. You remember, it's aiming for a similar level of precision eventually. They don't want to put landing legs on Starship. They want it to be able to get plucked out of the air by some equivalent device somewhere else. So yeah, by the way, there's 4 different cameras to watch for to try and figure things out. The left one, obviously, here is the...
So what we're seeing here is the COPV basically firing, I'm assuming. And it just gets everywhere. But it's firing to maintain attitude control or something.
The one that's mounted out on one of the fins pointing backwards at one of the rear ones. Whereas the one on the right, they actually are...
I guess not. I guess at this point it's already... This is plasma.
Cycling through different cameras. That is the rear fin right now looking from above. And
either plasma or actually air. I don't know.
I can't honestly tell you if the color that you're seeing on the top of that fin is due to the steel being heated and taking on like...
Yeah, these colors. Like, what are these colors? Reflection or heat?
Different colors, or if that's just simply reflecting different colors in the in the plasma around it. Also, take note of all those sparks. That indicates like pieces that are coming off the shield. It's ideally not supposed to happen, but they're still.
So the ablative, something is coming apart. Okay.
Working to develop the shield. Anyway, we know one of the fins is getting heated from below because we can see it now. Look at that image in the top left. That is definitely getting heated from behind.
Wow.
So this is the left forward fin, and it's not clear how.
This is the left forward fin. That's where the camera is located. Where's the camera? Is this the camera? The camera should be somewhere around here.
That is being heated from the other side, whether there's actually tiles are missing where that hotspot is, or whether there's tiles elsewhere and hot gas is penetrating through and specifically hitting that area. Now, the forward fins have a harder time sealing because they are attached to a curved surface. So the curvature is sort of naturally going to mean that when you're designing the seal, you're going to have points which are going to have higher pressures or temperatures, different conditions along there. But yeah, again, if you zoom back out, we have 4 cameras.
This is the left, where the camera is on the left forward fin. This is, what is this? This looks like the right back fin, the left back fin. What? The only one missing is the right forward fin, but it does look like the left forward fin. But that's where the camera That's where the camera is. We are at the left forward fin, so it's right below us. That is what is protecting the camera. So where's the right forward fin?
Views. On the left, you have the forward fin and then two of the rear ones. The rear ones are looking fine, but there does appear to be a small hotspot near the root. I was sort of worried about that, but it turned out that that wasn't really a thing that I should have been too concerned about. But then they swapped over to the right forward fin, and you can definitely...
How do you know this is... Why do they keep swapping? Why not show all of them? How do you know this is... Yeah, this is the right forward fin. Yeah, that makes sense. And its back part is being torched and at the joint.
They see at the root there has been hot gas penetrating, and that fin is starting to fail. So now we're in a situation where it's
terrible. Yeah.
starting to lose chunks of its control surfaces. But the good news is it's not as bad as we saw in the previous flight. But the question still remains: would it make it through the atmosphere? Well, now it's down to 45 kilometers. Its speed is down below 10,000 kilometers per hour. It's actually, you'll notice at this point, the heating of the plasma. There's a lot less light coming from.
1 second, let me plug my laptop. Nobody wants to join me in about 7 hours. Okay.
From the plasma around the rocket, and more of the heating is now thermal emission from the surface of the vehicle. It's basically slowed itself down. It's gone through max dynamic pressure. It has working fins.
I was afraid that we're losing the camera because of the torching, but it's probably because we're in the dark zone, because we're landing at night in Australia.
Can it get itself on target? Like, clearly the vehicle is holding a stable altitude. It's not lost control, but with the limits, with the damage.
She needs to, like, she could do beautiful things with her hair besides this. This is like, I mean, there's like, she's doing something much more interesting with her hair. Her hair, like, she's like such an engineer. Like, do something with your hair.
Damage to the fins, has it gone beyond the limits that will allow it to maintain its target? Again, looking at 4 times regular speed, you can actually see these fins moving back and forth very quickly, just carefully adjusting the attitude as it descends into the horizontal orientation. It's now descending at a subsonic speed, way slower than that booster did. This is the belly flop maneuver. It is a high drag orientation that lets it fall at a relatively slow speed, which means that it needs to slow down a whole lot less using its engines. They're giving it more propellant. Remember, the propellant for the landing burn is stored in those 2 small header tanks inside the much larger tanks. So yeah, see the engines lighting up. I love that you can actually see the reflection of the engine firing in that shiny.
And you see that it's now vertical.
Steel. It comes down. Now, they wanted it to land at a slight angle because they hope that they might be able to recover something for checking later. A lot of flashes as we get light underneath the water. The booster falls over, and then we lose signal. But all is not lost because the whole thing happened right next to a buoy in the middle of the ocean. Right? This had a camera on it. It was ready. We see a mushroom cloud of propellant just ascending up above there. I mean, sure, that was a violent end to Starship, but there are chunks left still floating in the ocean at this point. I'm not sure if they will be able to tell anything about the heat shield. But again, it is an awesome testament to the power of good engineering and design and people that make things want to happen. That this thing came through the atmosphere, had significant damage to its control surfaces. Not only did it touch down soft like the previous one, it did so on target. So I think both of these show massive wins for the guidance, software people. Clearly, the heat shield is still a massive problem that they need to solve. And while they have managed to catch a booster, that is a long way from making the booster fully reusable, rapidly reusable. And then, of course, going forwards, they're going to have to scale up Starship and Super Heavy so that it can perform the mission for which it was intended. So anyway, yeah, the absolute win on both of their accounts. There's a lot of work still left to do. And I think that if they're not...
Yeah, they need to grow. I think both the booster and Starship need to grow. They need to add more rings so both are longer.
Changing the flight profile, they might be able to actually very quickly proceed to another launch without changing the license. So now that all the risk mitigation factors have been demonstrated, I think we might get to the next flight a lot more quickly than we got to this one.
The question is, will they refly this booster? Probably not. Probably not. I don't think there's a point. Maybe to retest the landing.
I'm Scott Manley. Fly safe.
What duration of time, and if you want 90% accuracy, that means we can have like 5%.
Hello, it's Scott Manley here. In my most recent Deep Space updates, I talked about a company called Longshot, who are basically building a big gun which they think can be used to launch stuff into space. Now, I have actually previously talked about building big guns to launch stuff into space. In fact, I think that video is 10 years old now. It was made back in the era where all I was doing was playing Kerbal Space Program and trying to teach space science using that. And well, the problem with space guns is you can't do it in Kerbal Space Program, so I had to actually do a real science video. And so
it was kind of important because it was one of the first times I did science without actually using the crutch of video games to explain it. Anyway, I discovered that Longshot were based in Oakland, very near me, and I thought, it's a shame these guys didn't get in touch with me because I would have loved to have visited them. And I searched my Gmail and discovered that yes, they had in fact got in touch with me 2 years ago. And when you look at my inbox, you might understand why. This is not a Photoshop. And so a few days ago, I finally got to visit to remedy that oversight. I got to talk with their CTO. He explained how their system worked and why they thought that it was worth pursuing and how it might actually scale up from being a bunch of tubing inside a cargo container to being a 15-kilometer long system able to launch payloads into orbit. So if you know anything about regular guns, you'll
15-kilometer long? What?
explained how their system worked and why they thought that it was worth pursuing and how it might actually scale up from being a bunch of tubing inside a cargo container to being a 15-kilometer long system able to launch payloads into orbit.
15-kilometer long? But how do you aim it at the sky? How do you aim 15 kilometers at the sky? Like by a mountain or something?
So if you know anything about regular guns, you'll know that there is a chemical charge which generates gases and pushes the bullet down the barrel. And you can make the gun faster, basically by stretching the barrel so the bullet is accelerated for longer and increasing the size of the charge. But the thing is, there's actually a sort of fundamental limit in how fast a chemical charge can push a bullet using pressure. And this speed limit is based upon the speed of sound. Now, there's this paper which I was given a comparison of distributed injection, hypervelocity, and accelerators. And what it shows is when the bullet starts getting pushed down the barrel, it basically creates a rarefaction wave, the opposite of a pressure wave, but it's basically a sound wave that travels at the speed of sound and it bounces back and forth. And as the thing moves down the barrel faster and faster, this wave essentially gets weaker and weaker until it can't push it anymore. And if you have an infinitely long barrel, then you could get something up to 5 times the speed of sound. But for practical barrel sizes, it's more like 2 times the speed of sound in the gas. And the typical kinds of chemical propellants involved are generate gases like carbon dioxide, water vapor, nitrogen. And granted, this is hotter, so it has a higher speed of sound, but they're all kind of slow compared to, say, helium or hydrogen. And there are actually types of guns called 2-stage light gas guns, and these are used by like the vertical gun range at NASA Ames, where they're shooting very high velocity projectiles at targets to test orbital debris. What you have is a big chemical charge which pushes a piston, and then that piston pushes a hydrogen, and because the hydrogen is so light, the bullet goes way, way faster, like many kilometers per second. But that's not what Longshot is doing. Instead, their hypersonic accelerator is using a distributed injector system. And remember I said that if you had an infinite...
Why not use a magnetic accelerator? Isn't that simpler?
Long barrel, there's a speed limit. Well, one of the reasons why you're typically limited to about 2 times the speed of sound is because the gun gets inconveniently long as the gas pressure expands and drops. But if you keep on injecting gas, then you can make it accelerate faster over a shorter range. Now, you can't increase your ultimate speed, but you can shorten the gun barrel a whole lot if you continually inject in gas as it's being, as pressure is lowering inside the barrel. So this is what we have here, a multi-stage injector.
There's a new kick stage here. What we're doing here is we use that big kick stage out there. Right.
So they just keep injecting every time the bullet passes by. So right behind it, they just inject, they just blow up more charges. So there's always a shock wave behind the bullet. So it's always being pushed forward faster and faster. But they also need to continuously suck out. Well, it should be a vacuum. So the whole thing should be a vacuum, and every time the bullet passes by, they blow up a charge and create pressure. So there's always a pressure, high pressure maintained behind the bullet and a vacuum in front of the bullet.
What we're doing now is we're trying to make this thing into an exact scale model of the system we built out in Nevada. So what you basically got here is a cylinder which you cut the bottom off and weld it onto your pipe.
Weld the flange on it and then bolt it together with the pipe. Yeah. Okay. So this segment gets removed, projectile goes in, the segment goes back into position, everything gets bolted up. When we pop that first disc, projectile starts to move. You have a photo here. Yep. It's that projectile. It starts heading down the barrel. Vacuum pumps to pull the air out, and then this would be your first boost stage hypothetically. Yep, exactly. A lot of sensors here. We've got this is a high rate pressure sensor. We collected like a megahertz, and then photo gates and some strain gauges. So these are the things that we built. These are again cylinders, which those ones were custom made. But yeah, okay. So yeah, those ones are we custom made large volume boosters. So at one point we thought the problem was our boosters didn't have enough volume, so we were like, well, we'll solve that. We'll just make boosters that have a lot of volume. And it turns out that wasn't the problem. And we did some more analysis later that was like, oh yeah, we were being dumb. But anyway, that's so yeah, we've got another booster here, and then a third booster here, and another set of vacuum pumps down here. Yeah. And so the video I saw from a couple years ago said that you were like up above Mach 4 and you're aiming for Mach 5 in 2 weeks. And we didn't never heard Mach 5. Yeah. We've never done Mach 5. No, we got Mach 4.2 repeatedly. That's basically supposed helium and this architecture. Right. If we could use hydrogen, we could go faster. Or if we did side injection. So this is your test actual impact cell, right? Yeah. So we chicken wire, hit foam.
He's a little autistic. I can tell by the way he holds his hands.
Lots of bright lights. Yeah, like incandescent lights. High speed camera. Yeah, they're all LEDs. Okay. Yeah, that's for the high speed.
Yeah, you see his fingers? They're moving back and forth a little bit.
Yeah, because we're going 16,000 frames a second. Yep. And so there's not a whole lot of photons. Right. And your target is old bits of carpet and sheets of metal, I guess, in between. No, the bits of metal are actually pieces of the last projectile we shot. So that'll be great until you go fast enough that everything catches fire. Yeah, right? Oh, yeah, no, I mean, even at Mach 4.2, there's nothing recoverable. The projectile turns into a little bit. This is, yeah, what I mean is start fires. Oh, well, I mean, it already does. You can smell the carpet is slacked. Like there's, it's slacked.
No, I think he's normal.
The carpet, it's absolutely on burns for a moment when it goes. And I like, by the way, that I can see the concrete that you put in this safe. So you basically took this safe, it wasn't heavy enough, and you filled it with concrete wood, bolted your target case onto the front here. Yep. And if you look at the back, you'll see there's a dent. Concrete. Yeah, big outward facing. Big dent, yeah. And then down there's the shock absorbers that we ended up installing because this thing went up against the back of the shipping container and then started pushing the shipping container. Right. So yeah.
That's to let the gas out. We try to be considerate to our neighbors and muffle the noise. When we first started, we were saying car alarms, and now it's more like, oh, so we drop a load of bricks.
Right. So this is a much bigger one here.
Yeah. So we have 3 sort of big boosters, 3 what we call medium or normal size boosters, and then we also have 3 tiny boosters.
Right.
So we can, we're testing out different configurations and figuring out what.
So what pressure do these things run at?
Everything runs at about between 850 and 1,000 psi.
850.
850 psi and 1,000 psi.
Oh, 800. Okay. So like 60 amperes.
That sounds about right. That sounds about right. Yeah.
PSI is unfortunately.
Now, 850 psi or 60 amperes is actually very low compared to a regular gun that is firing off a chemical charge. But the fact is they're just putting a lot more gas in already, pre-expanded and pressurized, and it doesn't actually need that much pressure to accelerate to these speeds before it starts running into the limit of the supersonic sound limits. The real technical challenge is being able to trigger these boost stages as the projectiles travels down. You don't want to do it too early because then you will slow the thing down. You don't want to do it too late because then you will lose some performance. And since valves don't exist that can open this quickly with this much precision for this level of flow, they instead use burst discs, which are flat pieces of metal, and they cut a thin panel or pattern into them so that they will break in a well-understood way at a certain pressure, and then they help trigger this a little using a bit of trickery that generally involves high voltages applied to that face, and that way they can open these valves within milliseconds when they're needed. So yeah, they built this system and they're testing
Milliseconds, that's so slow.
it. They've been able to throw projectiles at Mach 4.5, and they basically demonstrated to
The human ear can hear in milliseconds, I think.
the Department of Defense that they know what they're doing enough, that they've got money or they've got a contract to build a bigger version that can throw projectiles fast so that science experiments can be done. Of course, hypersonics is all the rage, so having a gun that can lob projectiles at Mach 5 would be nice. And while that's the current project, they still are
Good tech.
talking about ultimately being able to launch stuff into space. And this design with those multiple injectors doesn't actually get them that far down this road because, as I said, there's a fundamental limit to their top speed. And even having this distributed injection...
Imagine like a ship, a long ship that has such a gun on it. And you can just fire projectiles at Mach 5 at incoming enemies. Wow.
Off the hydrogen or helium gas along the barrel, that doesn't actually help with your top speed. It just helps accelerate the object down the barrel and get it up to speed more quickly. So after a tour of the existing systems, we sat down with a whiteboard and talked about the plans to go from Mach 5 up to Mach 25, the kind of speeds that you would need to get into orbit.
Wow.
And look, the first stage starts out as one of these standard distributed injectors. It pushes the thing down the barrel, gets...
Obviously, the money is not going into beautiful offices. I mean, these people are like basically nomadic level office style.
Up to a certain baseline speed. But very quickly you get to a point where the projectile is just moving too fast down the barrel for the gas to keep up with it. And at that point, if you want to push it any faster, you can't, right? Except that there's a trick you can borrow from sailing, where if you sail boats, you may know that you actually sail across the wind, right? At right angles to the wind, you can go faster than the wind because sail down the barrel for the gas to down 25, the kind of speeds that you would need to get into orbit. And look, the first stage starts out as one of these standard distributed injectors. It pushes the thing down the barrel, gets up to a certain baseline speed. But very quickly you get to a point where the projectile is just moving too fast down the barrel for the gas to keep up with it. And at that point, if you want to push it any faster, you can't, right? Except that there's a trick you can borrow from sailing, where if you sail boats, you may know that you actually sail across the wind, right? At right angles to the wind, you can go faster than the wind because you place your sail at a relatively small angle and it acts like a wing. And their proposal is pretty much the same thing, but with a projectile. And instead of a sail, it has a big V-shaped boat tail on the back. And the boat tail is basically a triangular shape, and the gas comes from the side, hits it at an angle, essentially squeezes the projectile faster than the ultimate velocity of the gases that would otherwise, form the limiting factor.
I have no idea. What is he talking about?
This is not a new idea by any means, but Longshot have been working on getting these burst discs so that they can be triggered and burst at the right time so that you could actually push something down the barrel at many kilometers per second.
2 meter diameter, 3,000 kilograms, 500 kilogram payload. What does that mean? How big is our tail? Cool. So our tail is going to have, basically like if you read that paper, it gives you some of the...
I think people gave up on magnetic acceleration, magnetic rails, mag rails, whatever.
Around like what the optimal tail angle is. And that ends up being something like, 10-degree half angle. So we know the length of our tail, or like, we know an option that is probably close to ideal for the length of our tail. And we're going to want to fire these boosters.
That sounds ridiculous.
So that, say we get 90% coverage on the tail. So we fire the booster, maybe we miss a little bit here, and it's decaying at the end, and we get some profile, like here's what the pressure distribution of the tail is. So that gives us a timing regime where we can say like, cool, this tail is going to be passing the nozzle in what duration of time, and if we want 90% accuracy, that means we can have like 5% off here. So that, this whole thing turns out to be about a millisecond, and so this turns out to be about 100 microseconds. So we need basically much sub-millisecond precision on the timing of opening burst disc. And if you're like, okay, the burst disc takes 1 full second to open, but we can do that with 100 microsecond precision, we can make that. We can make that work. What's much easier is if you can just make the whole burst disc open in 100 microseconds.
Right.
Because then you can be like, oh yeah, cool. Well, we've got some variability, but it will always be opening less than 100 microseconds. So that's our target goal of how fast we want to open burst discs is basically 100 microseconds.
And by opening, you define going from like 0% to how much?
In this video, we're going to discuss how gravity can shift the frequency of light in general relativity due to the presence of a spherical mass, described by the Schwarzschild metric. This frequency shift ends up being similar to the Doppler effect that we saw in special relativity in an earlier video. The method I'm going to use to derive gravitational frequency shift in this video uses the wave covector. You might find this method to be a lengthy and roundabout way of doing things. But my goal here is to show that the Doppler shift from Galilean relativity, Doppler shift from special relativity, and frequency shift due to gravity can all be handled using the same approach for both inertial observers and non-inertial observers. We don't need to learn 6 different approaches and treat all of these as separate special cases. Just as we measure momentum and energy in different frames by measuring different components of the forward momentum vector in different reference frames, all we need to do to understand frequency shift is to draw the wave covector and then look at how different frames measure different components of the wave covector, and this will work every time in all cases. At the end of this video, I'll do a comparison between gravitational frequency shift in general relativity and Doppler shift in special relativity for non-inertial observers, and I'll talk about how these are related to the equivalence principle. In the Relativity 106a video, we saw that understanding the Doppler effect becomes very easy when we use a geometric object called a covector. As a reminder, a vector is like an arrow, and it represents something with a direction and a length. Meanwhile, a covector is like a stack, and it represents something with a direction and a density. Vectors are useful for giving geometric representations of things like position, velocity, acceleration, momentum, and force.
So this is good for topology, for the curvature of space-time, I guess.
And covectors are useful for giving geometric representations of waves, which have a direction and a density. A wave covector's density in time is the wave's frequency, and the covector's density in space is the wave's wave number. If we take a space-time diagram and imagine a wave traveling left over time, we can visualize the wave as a surface whose peaks travel left. We can then trace lines over the wave peaks to get our wave covector stack, which we'll call kappa. If we have a sound source creating a wave in space-time, we can measure the sound wave's frequency in different frames just by counting how many covector surfaces are pierced by a reference frame's unit length basis vector. For example, Einstein's time basis vector pierces 2 wave fronts, so he observes a wave with a frequency of 2 Hz. But the car's time vector pierces 4 wave fronts, so it observes a frequency of 4 Hz. This is according to Galilean relativity, where we only tilt the time axis to change between inertial frames. For special relativity, we use the Lorentz transformation, which causes the time and space axes to move together like a pair of scissors. If Einstein observes this light wave to have 1 frequency, the car, which is running toward the light source, will pierce more wave fronts with its time basis vector.
It's good to see this, so I know where we're heading when we're learning GR, because I mean I've seen this is like tensor analysis. Is it? It looks like a little bit of like the coefficient of the basis or something. Maybe that's how it's used. I don't know. Are these tensors? I don't know. But okay, this is the time dimension and the space dimension. This is the original. This is the transformed. So he's, I guess, this is the moving car. Like scissors, like through space and time. I don't know. Why would it be? This is a wave moving to the left, so the wave is moving to the left. Why is it at an angle? I don't know.
So it observes a higher frequency, meaning the light is blue shifted. Similarly, if the car is running away from the light, its time basis vector pierces fewer wave fronts, and so it observes a lower frequency, meaning the light is red shifted. From these geometric observations, it's easy to derive the formula for the relativistic Doppler shift of light, as we did in Relativity 106.
All right. We need to continue with tensor calculus.
Hey everyone, welcome to this new video series I'm doing on tensor calculus. So in this introduction video, I'm going to answer 3 questions you might have. What is tensor calculus? Why would you want to study it? And what do you need to do to get started learning tensor calculus?
My left ear thanks you so much. How many comments? Five years ago. No one mentioned my left ear thanks you? Let's see. Left side. My left ear enjoyed it. Yes. That's the most important comment. Nothing else is important.
Well, to answer what tensor calculus is the study of how tensors change over space. So before getting into the calculus, let's take a moment to review tensors. So if you've watched my Tensors for Beginners series,
change. Okay.
You'll already be familiar with a bunch of different types of tensors. You'll have seen vectors, which are like arrows, covectors, which are like stacks, linear maps, which are spatial transforms that keep lines parallel and evenly spaced, and the metric tensor, which is like a machine for measuring lengths and angles.
So this tensors for beginners. Where's tensors for beginners? Where is tensors? How do I get back? How do I get back? How do I get back? This is this video. Show less. Re-upload after I caught a small mistake soon after uploading. Okay. Where is tensors for beginners? Tensor calculus. Tensor eigenchris. Playlists. Close this. Tensors for beginners, 18 lectures. Did I do this?
All right, welcome to this video series on tensors. In this first introductory video, I'm going to try and give you a bit of motivation for why you might want to study tensors, and then in later videos, I'll get to explaining what tensors actually are. So before I start, I should mention that I expect people watching this video series to have a little bit of linear algebra under their belts already. So I'm hoping you already know how to multiply matrices.
I think I already did a lot of it, and I got stuck somewhere and switched to another teacher. Because everything here was pure math, and I just didn't know where he's taking this course.
And you know what terms like linear combination and dot product are. If you don't know any of this stuff, you're welcome to watch anyway, but you might find it a bit harder to keep up. What I'm going to try and avoid doing is doing any mention of calculus. Some people like to introduce tensors using calculus, but you really don't need that. You only need linear algebra. I'm going to talk a little bit about calculus and tensors at the end of the video series for people who do have a calculus background, but I'm going to do my best to avoid any mention of them until then. All right, so why should we want to study tensors? So the main reason you would want to study tensors is geometry. If you understand tensors, then you can get a lot of insight into how geometry works. Now, I'm not talking about the geometry you would have learned in elementary school or high school, stuff like basic shapes or trigonometry. I'm talking about geometry that can be fairly complicated and not very intuitive. So one example of such geometry is the geometry of space-time in Einstein's general relativity. So let's talk about that a little bit. So if you've ever read or watched any popular science articles or videos on general relativity, you've probably heard about how space-time is curved and how light can travel in a curved path around massive bodies like stars and black holes. Another thing you might have heard about is how the universe is expanding, right? So at the beginning of time, we had the Big Bang here, and ever since then, the universe has been getting bigger and bigger, and so the universe is expanding. Now, when you first hear these ideas, you're probably thinking, what the heck do these even mean? What does it mean for space-time to be curved? What does it mean for the universe to be expanding? So in order to understand these ideas mathematically, we need tensors. So I'm just going to throw up some equations on the board right now. So these are Einstein's field equations. And I say equations with an S on purpose because even though it doesn't look like it, there are actually 16 equations here. And these 16 equations tell us how space-time is curved and why the universe is expanding. Now, you don't need to understand what any of these symbols mean, but the important thing that I'm going to point out to you is that every symbol that I'm underlining right now is actually a tensor. So there are tensors everywhere in these equations. And the most important tensor in general relativity is this one here, the G, which is called the metric tensor. It's a 4x4 rank 2 tensor, which you could also call a 4x4 matrix, and it helps us measure lengths and angles in the curved geometry of space-time. Now, I'm going to talk about the metric tensor in, I think, video 7 or 8. I'm going to use much simpler examples than the ones you'd see in general relativity, but hopefully you'll understand what the metric tensor is, and you'll take in the first few steps toward understanding why space-time is curved and why the universe is expanding. All right, so another example of tensors being important is in quantum mechanics, and in particular, quantum computing. So quantum computing is a pretty active field of research these days. If we ever get quantum computers working, they'll be able to solve some problems that the classical computers we use today are not able to solve, or at least the classical computers we have today can't solve them very efficiently. Anyway, again, if you've ever seen popular science articles or videos on quantum mechanics, you've probably heard the term quantum superposition. And so this is the idea that quantum systems can be in two states at once. And usually they give some weird example involving a cat being dead and alive at the same time. I'm not sure how literally you want to take that, but there it is. And so another idea in quantum mechanics is the idea of quantum entanglement. And so this is the idea that two particles can become entangled, and even if you separate them by hundreds of kilometers, they can still influence each other in strange ways because they're connected using this strange quantum entanglement property. So again, what do these terms even mean? What's quantum superposition and what's quantum entanglement? What do these mean mathematically? So it turns out that superposition, if you know a little bit of linear algebra, superposition is just a fancy way of saying linear combination. So with linear combinations, what we do is we have what you might think of as simpler vectors, and we combine them together using scaling constants and addition to get a more complicated vector here. And it turns out in quantum mechanics, physical quantum states are actually just vectors. And so we can combine simpler states together using linear combinations to give us more complicated states. And so that's really all quantum superposition is. As for entanglement, when two quantum systems are entangled together, what we really mean is that the state vectors have been combined together using something called the tensor product. And that's what this circle X symbol is. It's the tensor product. So what the tensor product does is it takes the geometrical space where the first system lives and the geometrical space where the second system lives and combines them together to create a more complicated geometrical space. And that's where the entangled system lives. So I'll be talking about the tensor product in, I think, video 9 or 10. And hopefully that will be a first step toward understanding quantum entanglement mathematically. All right, so hopefully I've made you at least a little bit curious, and hopefully you want to learn a little bit more about what tensors are. In the next video, I'm going to start explaining what tensors actually are, and after that we can get started learning some actual math. So I'll see you in the next video. All right, so welcome to this second video in my series on tensors. In the last video, I tried to give you a few reasons for why you might want to learn about tensors. In this video, I'm going to try and explain what exactly tensors are. So tensors are a little hard to describe if you've never heard of them before. So what I'm going to do is I'm going to give you several different definitions that you might hear from different people when you ask them what a tensor is. And hopefully seeing all these different points of view will put you in a good starting position so that you feel comfortable when we actually start doing real math in the next video. Okay, so let's get started. Here's a first attempt at a definition for tensors. I'll just read it off. So a tensor is a multi-dimensional array of numbers. And by array, I basically just mean grid. So a grid of numbers. Okay, so let's see some examples of what this might look like. So the simplest example of a tensor is what we would call a scalar, or sometimes a rank 0 tensor. And a scalar is basically just a number. So any number like 1, 2, 5, 3/4, pi, these are all examples of scalars. And we don't normally write scalars as arrays, but if we wanted to, we could write little square brackets around the scalar like this and sort of pretend it's an array, but we don't normally do that. All right, so those are scalars. Another example of a tensor you've hopefully seen before is a vector, or a rank 1 tensor. And we call it a rank 1 tensor because it's a list of numbers that extends downward in one dimension. So it's like a one-dimensional array. So that's a vector. Another example you've probably heard of are matrices, or rank 2 tensors, and we call them rank 2 because they are a two-dimensional grid of numbers, so they extend up, down, left, right. And if you recall from the last video, I mentioned that the metric tensor from general relativity is a rank 2 tensor. And these little Greek letters that you see here actually stand for numbers that represent the row and column of the particular entry of the matrix that we're talking about. So the metric tensor is really just a matrix. And we can go higher and higher. This is a rank 3 tensor because it's in a three-dimensional grid of numbers sort of arranged in a cube. And we can go on and on, rank 4, 5, 6, as high as we want. So any multidimensional array of numbers is a tensor. So I call this the array definition of tensors. Okay, so I said that this was a first attempt at a definition, and it does give us some idea of what a tensor is, but this definition is actually wrong, and here's why. So tensors can be represented as multidimensional arrays, but that's not what they fundamentally are. Tensors aren't just a bunch of numbers that we toss together. Tensors actually have real geometrical meaning, and if we just think of tensors as these multidimensional arrays, we sort of miss out on the geometrical meaning behind them. So if
okay, no comments, nobody's with us. It's fine. It's fine. We need to figure out tensors.
we casually toss the word tensor around to mean a multidimensional array of numbers, that's sort of fine. There's nothing wrong with that. But if we're thinking seriously like mathematicians and we want to understand geometry, this definition, the array definition, is simply just wrong. So it's no good to us. Okay, so let's try again. So here's another attempt at a definition. I'll just read it. A tensor is an object that is invariant under a change of coordinates and has components that change in a special predictable way under a change of coordinates. Okay, so that's certainly a mouthful. So what does that mean? So let's start with the top part. What does it mean to be invariant under a change of coordinates? Well, to explain that, I'd like you to try picking up a pencil and point the pencil toward the nearest door that you can see. So there are a few things that we can say about this pencil that are just facts, and they don't depend on any coordinate system. So for example, the length of the pencil, the length won't depend on our choice of coordinate system. The length is an intrinsic or invariant quantity. Also, this pencil is pointing toward the door, and that's just a fact. It doesn't depend on what coordinate system we use. The pencil's orientation is intrinsic or invariant under the choice of coordinate system. Now, the second part, what does it mean for components to transform predictably under a change of coordinates? Well, to start off, let's introduce a coordinate system here. So we have a nice 3D coordinate system with 3 vectors here that give us the main coordinate directions. And what we can do is we can measure the pencil using this coordinate system. All right, so it looks like this pencil is made up of 2 yellow arrows, 1 green arrow, and then 2 blue arrows. All right, so we can write this pencil as a linear combination of the coordinate vectors here. Okay, so what we just did here by breaking down the pencil into the coordinate vectors is we measured the pencil's components. The components are just the amount of each coordinate vector that we need to construct the pencil, right? So with this coordinate system,
notice that you can use the green, but you don't have to. You can use more of the green, less of the yellow and the blue. So there's many ways you can construct a vector using a tensor representation. Right? I don't know. Or is it a 3D and there's only one way? Is there many ways to represent a vector? Probably. Probably, right?
system, the components are 2, 1, 2. Now, I introduced this coordinate system here, and you might think it's a pretty sensible coordinate system because all the direction vectors are the same length and they're all perpendicular to each other, so that's kind of nice. But really, there's nothing special about this coordinate system, right? I could just as easily introduce another coordinate system like this, where the vectors are all different lengths and they all sit at weird angles relative to each other. But mathematically, neither of these is more correct than another. They're simply just different choices. And so with the second coordinate system, I can sort of do the same thing. I can measure the pencil along each coordinate vector, and I can see that this pencil is made up of 2 black vectors, 3 purple vectors, and then 1 red vector. And again, I can write the pencil as a linear combination of these vectors, and I get the components 1, 3, 2. So you'll notice when I measure the pencil using different coordinate systems, I actually get different components, right? And this is a really important idea. The pencil's components are not invariant, right? They change depending on the coordinate system.
And you can probably have different components to represent the same vector with the same basis.
Okay, so the pencil is
vectors. Vectors are invariant. Vector components are not invariant. Right? The vector, well, okay, the vector itself, like the pencil, is invariant. The components are not invariant. What do you mean by that? Like when you change a coordinate system, of course, the components, well, it's different components, but it's also different basis vectors. That's what it means to change perspective.
Invariant, but the coordinates are not invariant. Okay, and again.
He said coordinates, but he wrote components.
They use. Okay, so the pencil is invariant, but the coordinates are not invariant. Okay, that's a very important idea. So now,
Very dangerous to learn from someone who writes one thing and says another thing.
it turns out that if we know how to change one coordinate system into another coordinate system, right? So if we know how to go back and forth between these two coordinate systems, then we should also be able to figure out how to change back and forth between these different sets of components. And this process of going back and forth between coordinate systems and components, that's what I'm going to call forward and backward transformations. And I'm going to talk about those in the next video. All right, so backing up, what a tensor is an object that is invariant. It doesn't depend on a coordinate system, but its components, which do depend on the coordinate system, change in some special predictable way that we can figure out using these forward and backward transformations. And this is what I'm going to call the coordinate definition of a tensor. And this definition is actually pretty good. It does get to what the heart of a tensor is. It's an object that's invariant, but whose components change. But it turns out that we can come up with an even better definition. And so I'm going to switch to that one here. So here's our third final definition. I'm just going to read it off. A tensor is a collection of vectors and covectors combined together using the tensor product. So this definition ends up being really nice. It's really short and sweet. There's just one problem. If you've never studied tensors before, you may have heard of vectors, but you've probably never heard of a covector, and you've probably never heard of the tensor product. So the downside of this definition is that we need to put in a little bit of work before we can even understand what it means. But once we understand what all these things mean, it's actually a really simple definition. Tensors are just vectors and covectors combined together in different ways using this thing called the tensor product. So this is what I call the abstract definition of a tensor. So this is really the best definition of a tensor we can come up with. And I'll get to this definition later on in the video series once we have the basics down. All right, and I have a little bonus part here. So for those who do have a calculus background, I'm going to talk about how tensors pop up in calculus. And that's when we see tensors as partial derivatives and gradients that transform with the Jacobian matrix. So you can skip this section if you aren't feeling very strong with your calculus skills. It's an extremely interesting use of tensors, and it's very important for the curved geometry we might see in general relativity. But if you're not comfortable with calculus, you can feel free to skip over this part. All right, so this is sort of the end of the introduction. I spent the last two videos just sort of preparing your brain for what tensors are. In the next video, I'm actually going to start doing real math, and we're going to start with forward and backward transformations. So I will see you in the next one. Welcome to this first real video in my series on tensors. The previous two videos were mostly on giving motivation and background on tensors. In this video, we're going to get started doing some actual real math. So the first thing we're going to learn is forward and backward transformations. These are the rules that let us move back and forth between different coordinate systems. I mentioned in the previous videos that tensors are invariant under a coordinate system change. So understanding how to move back and forth between coordinate systems is going to be really important for understanding tensors. Okay, so let's start off with the forward transformation. So I have two two-dimensional coordinate systems here, the old basis E1 and E2, and the new basis E1 tilde and E2 tilde. So remember from linear algebra that the word basis just means a set of vectors that give us the main coordinate directions for our space. So we have the old and new coordinate systems, or the old and new basis. So the forward transformation will move us from the old basis to the new basis. So how does that work? Well, all we need to do is build the new basis vectors out of the old basis vectors. So let's start with E1 tilde here. How do we build E1 tilde out of E1 and E2? Well, it looks like we need two E1 vectors and one.
He's not giving any motivation. Like, where is he going with this? This is so terrible. He's putting my brain to sleep. Let's check this guy out.
A few weeks ago, I was on Netflix.
So I told him I would love to debate you on this topic. You are wrong about everything. So this is which topic? Also, please correctly state my position. Don't waste my time. Do you want to debate me? Let's debate. You not want to debate me? Let's not debate. Your position is ban porn. And he's going to deny it. What do you call it? The benevolent king, the philosopher king. So I told him, your position is ban porn. Porn is bad. People are dumb. I am smart. I need to run the world. I'm a philosopher king. The masses are too dumb to allow them freedom. Freedom is bad. I hate America. I'm voting for Kamala. LOL. Let's debate already. He said, which topic? Also, please correctly state my position. Oh my god. What a leftoid. Go to hell. Go back to hell, leftoid. Oh my god. I hate leftoids. Communist. I forgot to say I'm a communist. Communism is the best. I asked my viewers to critique me. Here's how it went. Wow. Tensor analysis. Let's see what she says.
Hello. So, I was going to go to sleep. Well, I was going to go to sleep, but I'm not tired enough just yet, so I made a cup of tea, and while it's cooling down, let's talk about some math.
And while it's cooling down, why did you make tea and now you're cooling it down? So, okay, I mean, I found a way to drink my drinks when they're super hot. There is a way without hurting your mouth. Let's see. But your audio is so low.
Content. It's just us hanging out, me talking about math. So grab your cup of tea. I don't know, do something in the background or just hang out with me. I'll tell you about an exploration that I did in math. As you know, I'm trying to get myself to learn math again. In a more fun, creative way, following my curiosity now that I'm out of school. And so what I did about 2 weeks ago was starting with calculus. The calculus itself isn't exactly the point, but I needed to start somewhere, right? The way I really want to fuel my exploration in math is with my own ability to create questions and to explore those. But I need some material to create questions out of. And so we got to start somewhere and figure this out along the way. So I started doing the calculus course in Khan Academy, and their first unit is about limits and continuity. And there's a lot of, clear explanation about how to do limits and continuity. But first, I want to point out that there's some important quotes in some of these videos that Sal shares that is important beyond calculus itself. One of them is Sal was explaining this function, and he says this is a bit of a bizarre function, but we can define it this way. You can define a function however you like to define it.
I'm on maximum audio and I can barely hear her with my headset on.
And this is all of math, right? The whole point is that we can define anything however we want to define it, if it aids us in our exploration or in a proof or something, right? So we have all this freedom in it, and we get to pick what numbers we try or don't try.
Hello, folks, and welcome to Space Time
Jesus Christ.
with Einstein. I'm Brian Roberts. In the last video, we talked about how special relativity is built out of just two postulates, the principle of relativity and the light postulate. But why on earth would anybody believe these things? In this video, we'll talk about Einstein's pathway to special relativity. Einstein reports starting his work on special relativity at the age of just 16 in 1896, and a couple years later, he started on a massive 7-year journey to develop what is now the special theory of relativity. It was published in 1905 in a rather unassuming title. The paper was not called An Incredible New Theory of Space and Time. It was called On the Electrodynamics of Moving Bodies. It's in this article that Einstein formulates relativity in terms of these two principles. He formulates the principle of relativity, and he formulates the light postulate. Now, the principle of relativity is not actually so controversial. Even Galileo believed that it was true. The laws of physics are the same in every reference frame. It seems to be true every time we travel on a boat at constant speed in a straight line. It's just hard to tell we're even moving. The laws of physics appear to behave just as if we were at rest on Earth. What's harder to believe is the light postulate. Why on earth would we say that the speed of light is the same in every reference frame? That's really different than just about everything else I know. I turn on a flashlight at rest. Light moves 186,000 miles per second. Now put me in a moving train, and suppose I point the flashlight in the direction of motion and turn it on, the speed of light will again be 186,000 miles per second. It's the same in both reference frames. That's really strange. So why did Einstein say this? It's not automatic. Let's think about what else Einstein could have said. Einstein could have said that the speed of light depends on the speed of the emitting device, like flashlight. How fast is that device going? That's what determines the speed of light. Or he could have said that there's a special reference frame and that the speed of light is always
good. Yeah, very good. Finally, this guy's a science philosopher. Finally, someone is actually, stating the obvious. Finally.
fixed in that reference frame to be, say, 186,000 miles per second. Einstein thought about both of these ideas extensively. The first one is called an emission theory, and the second one is called the ether theory of light. Now, we know that Einstein extensively studied the emission theory and just couldn't make it work. But there's a simple little thought experiment that illustrates this, as pointed out all the is that device. Let's think about what else Einstein could have said. Einstein could have said that the speed of light depends on the speed of the emitting device, like the flashlight. How fast is that device going? That's what determines the speed of light. Or he could have said that there's a special reference frame and that the speed of light is always fixed in that reference frame to be, say, 186,000 miles per second. Einstein thought about both of these ideas extensively. The first one is called an emission theory, and the second one is called the ether theory of light. Now, we know that Einstein extensively studied the emission theory and just couldn't make it work. But there's a simple little thought experiment that illustrates this, as pointed out by Professor John Dean Norton. Einstein came up with this thought experiment when he was just 16 years old, and it's one of his most famous ideas called the chasing the light beam experiment. We imagine Einstein chasing a light beam, and he says very clearly what he thought about that. He said, if I pursue a light beam with the velocity c, the velocity of light in a vacuum, I should observe such a beam of light as an electromagnetic field at rest, though spatially oscillating. There seems to be no such thing, however, neither on the basis of experience nor according to Maxwell's equations, where Maxwell's equations are just the classical theory of electricity and magnetism and light. Einstein says that if you were moving in the same direction at the same speed as light, you'd see a very strange thing, a frozen light beam. And we never seem to see that. Has anybody seen my frozen light beam? But if the emission theory were true, we should be seeing frozen light.
Interesting. Because we're moving. Like if you think about it, we're moving. It should happen that because some emitters are moving away from us at the speed of light, the light reaching us should be standing still. It wouldn't wave, or it would wave in a different frequency, but that's just color. But the speed, why is the speed a constant? It should be the same color, but it's really weird. Like, how would it even work? It would appear to have mass. That's what it would appear to. That's like an electron, basically. That is not really, sort of, but it would be weird. So he said because it doesn't make any sense, therefore it's wrong, which is fantastic. That is how you should live your life.
Light beams all the time. The reason is there are all kinds of things hurtling through space producing light. There are stars all over the place, moving in every which way at every which speed.
Correct. So some emitters should be moving away from us and towards us, and that should change the speed of light if it depends on the emitter.
And so you would think that the light from some of those stars, when it reaches us here on Earth, might be frozen, or at least dramatically slowed down. But that's not what we observe. Every time we observe the speed of light, it seems to be the same, 186,000 miles per second in a vacuum. So this chasing the light beam thought experiment helps explain why the emission theory is.
So whatever light we use in order to run an experiment where we test the speed of light, like we use that thing that rotates with the teeth, right? We could use that. We could use the light that is incoming from a far star, but we always get exactly the same velocity. So all light seems to travel at the same velocity, which is bizarre. So it doesn't depend. Well, but it's a wave. I mean, the fact that it's a wave, it should tell you there has to be ether. I mean, that has to be your assumption. I don't understand why you would think otherwise. You need to rework physics around the ether. You have no choice about it.
Implausible. If the speed of light is just determined by the source, then we ought to see frozen light beams a lot more commonly. The second option, that the speed of light is 186,000 miles per second in one special reference frame, was actually the most popular theory at the time. Most scientists at the turn of the century believed that there was a nearly invisible, almost undetectable fluid filling all of space. It was called the luminiferous ether. You should think of light in the luminiferous ether as just like waves in the sea. To have waves in the sea, you need some sort of liquid for them to pass through. And the thinking was the same for light. To have light waves moving, you need some sort of liquid for that light to travel through. That liquid was called the luminiferous ether. And whatever frame of reference that ether turned out to be in, that was the special frame of reference in which light travels at 186,000 miles per second. But wait, which reference frame is that? If I can't detect the luminiferous ether, how can I tell which reference frame it's at rest in? This is invisible stuff surrounding me, but I don't know if it's in motion with respect to me or not. I always travel in the reference frame of the luminiferous ether. Why do people believe in something that they couldn't see? Well, we do it all the time. You believe in the dark side of the moon, don't you? Sometimes a concept is helpful to explain something, even if we can't see it. And in this case, this was the only way we could understand waves. But the more Einstein thought about the luminiferous ether, the more he became skeptical that it might not exist at all. And if
there's no such thing. You can't conclude it cannot exist. You can conclude that it's completely undetectable. You can postulate that it's undetectable. That's fine.
Luminiferous ether, there's no way to say that that's the reference frame in which light travels at its fixed speed.
Wait, what's the reason?
Einstein would be helpful to explain something, even if we can't see it. And in this case, this was the only way we could understand waves. But the more Einstein thought about the luminiferous ether, the more he became skeptical that it might not exist at all. And if there's no luminiferous ether, there's no way to say that that's the reference frame in which light travels at its fixed speed.
Why did you just erase it? You can be skeptical. It's not that Einstein never said there is no ether. He just said it's superfluous. He never. You don't erase it. He just said I don't need it, whether it's there or not. I don't care. That's Einstein. You misunderstood Einstein. He never said it's not there. Show me where Einstein said there is no ether.
The more I became skeptical that it might not exist at all, and if there's no luminiferous
No, that does not exist. Einstein never said that. You're putting words into Einstein's mouth.
there's no way to say that that's the reference frame in which light travels at its fixed speed. Einstein would be forced to the light.
No. Einstein said it's superfluous. I can do without it. That's it. Maybe there is, maybe there isn't. I can do without it. I can just ignore it. I don't need it for my theory. Maybe it's there, maybe it's not, but maybe it is there. I don't care. It could be there. My theory is still correct. That's Einstein. It fits the ether. There's no contradiction to the ether. Einstein never said there's a his theory contradicts the ether. Let's get the wording. Where's Einstein? What kind of a philosopher are you? I don't know what he means by these words. The introduction of a luminiferous ether will prove to be superfluous inasmuch as the view here to be developed will not require an absolute stationary space. I just don't require it. Doesn't sound like it contradicts him, provided with special properties, nor assign a velocity vector to a point of the empty space in which the electromagnetic processes take place, whatever. So, I can't select the whole thing. I can't. Oh, okay. Can I do that? Can I copy this? Copy. You're supposed to be a philosopher. What kind of a philosopher are you? 73 comments. Did anybody point this out? How would you detect a frozen light beam? Relativity is just an optical illusion? No, it's not. Wow. So this is Einstein, 1905, in his paper. Let's just say Einstein. Oh, Einstein. Oh, Einstein. Preceding, schmeceding, nor assign. The introduction of a luminiferous ether will, well, we can just comment. I think it will remove the spaces. Oh, it doesn't remove the spaces? The introduction of a luminiferous ether will prove to be superfluous, inasmuch as the view here to be developed will not require an absolute stationary space, will not require, nor assign a velocity vector to a point of the empty space in which electromagnetic processes take place, whatever that means. But he didn't say, so he didn't say there is no ether. He said, I don't require ether for my theory. Einstein did not exclude the ether theory. He merely theory. Shut up, Siri. Shut up. Shut up. Go to hell. Einstein did not exclude the ether theory. He merely did not require it for his theory. The ether theory might be correct. Jesus Christ. And so I would say both the ether theory as well as the special relativity theory might be correct and not contradict each other. Why? I think that's enough. So this is Einstein in his original 1905. I mean, this is literally in the paper. I can't. La 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 la. This is Einstein in his original paper. Stop. This is Einstein 1905. I think we should put it after the quote. So we start with the quote, but first we need to say the time stamp. The time stamp is 5:30. 5:30. Then the quote. At the end of the quote, we'll put the source. So Einstein did not exclude the ether theory. Do you understand? So Einstein did not exclude the ether theory. He merely did not require it for his theory. Right? And he says, will not require. So we can quote, will not require. Let me edit. Maybe we should put in caps. Will not require. I mean, what part of will not require did you not understand? Merely not require. Let's put not require. So not require. Which part of not require did you not understand? I Which part of not require did you not understand? It's compatible. SR is ether compatible. According to Einstein. How do you spell compliant with an A? Compliant. Oh my god. People are so weird. Didn't I send him an email? I want to show the room this point. I wonder what they're going to say. Like, this is a good... The room.
Yeah, I've heard that too. So, but the magnetic field bit's interesting because the three moons they're speaking of, they have a resonance with each other. One's like 2 to 3, the other's 1 to 5, and the middle star gets tugged. Middle moon gets tugged in and out, and the flex and contraction expansion on its outer shell creates the friction that's creating all the volcanism that's melting the water and giving it an ocean. Hence, possibility of life in simpler forms. So yeah, it's a really interesting little system. It's a system within a system. I love it. I get a space boat out of that shit.
Well, Jupiter is so, magnetic and radiation that the probes go in highly elliptical orbits. So they get near Jupiter, and then they whip around, and then they can spend a couple of months out in the safe zone. Because it takes extra hardening and all that shit. And so Jupiter is space probes. Oh no, we don't send anything anywhere. I mean, that's not possible. Well, I don't know what I was thinking.
That's all the conspiracies. You've been lied to, as Brian Mabbitt's been telling us for years now.
Yeah, getting data from Galileo. Yeah, that doesn't happen.
Yeah. What Brian Mabbitt's been telling us for years now, in between blowing up tires and delivering the media and newspapers that he actually denies are true. It's kind of ironic, isn't it?
Hey,
it's the media.
Hey guys, can I bring up something for a second?
Oh, you well. Is it a chicken bone? Did you not eat well?
What?
Can you bring up something? Okay.
Bring up.
You don't try humour on Mr. Slave.
Sorry, I just realised
He doesn't.
No, someone.
He doesn't understand humour.
Yeah, they turned it off. The button's been turned off on the back and glued shut. Okay.
So anyway, I posted like a quote from Einstein's original 1905 paper, both in the side chat and in what?
I've got an even better one for you.
What? I can't hear you.
I've got an even better one for you. Check this out.
Like what?
Well,
What?
I admit that the general theory of relativity is closer to the ether hypothesis than the special theory. This new ether theory, however, would not violate the principle of relativity because the state of the G nu mu equals ether would not be that of a rigid body in an independent state of motion, but every state of motion would be a function of position determined through the material processes.
What? When is this? Are you reading from Einstein?
In a letter to Lorentz on June 17th, 1916.
Right, that's 1916. There's plenty of times where he mentioned the ether. I'm just saying that even in the original 1905 paper, like people would say, "Oh, he changed his mind." So the answer is no, he didn't change his mind. He never discounted the ether theory. Like even in the
Why should he?
like
Why would he have?
well, look, when you talk to people, they say like they discount the ether theory as if
Yeah.
it's been disproven.
Well, so relativity's been validated. You don't have to disprove all models if only one has been validated.
But there's no contradiction. Einstein didn't feel, and I don't feel, that there's a contradiction between SR and the ether model.
Yeah, I know, but so there's an infinite amount of models that you can make on any subject. This is literally true. It's a problem of underdetermination. And if one of those models is validated, then that means all the other models could still potentially be true. It's just that they haven't been validated or disproven yet. So why should Einstein invalidate anything or not, or say ether can't be true if he's a scientist that knows that all theories are true until proven not to be true? Well, sorry, possible until proven not to be true.
I'm not sure what you're saying. So a lot of
It's pretty simple. Underdetermination, if the tree falls in the woods, there's a million reasons why the tree falls in the woods. You come up with a hypothesis, it's tested. If it's validated, that's the only hypothesis that is valid, and the rest could be valid if they could also make predictions that could test their hypothesis.
Well, I don't. So you're saying that all theories are equally valid always?
No, all theories are equally valid until they're either validated. So that means that there's a prediction that they've made that is true, or they are disproven.
So, okay. So before you said there's an infinite number of explanations to every event or something?
100% correct, yes.
Okay, but there is an infinite number of explanations, even though some are invalid. Some explanations, like to any one event, you're saying there's an infinite number of explanations, but some are invalid.
Yeah, some are. So what you do is you come up with a hypothesis for why that event happened, the cause, and then you come up to a prediction or an experiment to test the cause.
No, just yes or no. I'm just trying to, honestly, just trying to understand you. So is that what you're saying? I'm just trying to understand. I'm not, this is no trick. It's not a trick question. So you're saying that for every event, there is an infinite number of theories that are valid, but some of them are invalid. I mean,
you start out with the infinite number being valid, and then you weed them out. You come up with some metric to look at the one being more probabilistically valid than the rest, or discounted because the least likely because they've come up with something that invalidates.
I'm just trying to formalize what you're saying. So you're saying for every event, there is a set of explanations, an infinite set of explanations. There's a subset of that. There's an infinite subset of that of valid explanations. And there is maybe also another infinite subset that are invalid explanations.
Why did you use the word infinite 3 times?
Because it's an infinite set, which is composed of two
Not
infinite.
infinite, no.
Wait.
Yeah, it's a finite. It's a
Wait.
finite set. It's a finite
Mr.
set,
Slave.
and then you go through the game of process of elimination, and until you end up with the most likely or a very small set of highly likely.
Okay.
So
I'm just trying.
you're at a conference, and and 50 scientists present 50 different theories, and then they all talk about it, and by the end of the day, only 5 are still standing.
Okay. Look, I'm just trying to formalize what he said. I don't have a position.
I know, and it's a finite set.
It's a
and
finite
then you get
set?
subsets.
So it's a
Yeah,
finite set.
so I'm going to explain it just as philosophy because Shoebill's explaining it in the real world, which potentially better, but I don't think you can engage with the real world. So if you have an infinite set of possible things, and then you have a metric that can weed out that infinite set to finite sets of valid and invalid things, then you can come up with what is the most likely, the most probabilistically true, and that is something that has not been invalidated, that has also had some prediction that has been validated, or an experiment to show some link between cause and effect.
Okay.
Okay?
But you started with infinite, and then you said the two subsets that compose it are both finite, so that's impossible. So if you start with an infinite set, it has to be composed of some infinite subset.
It's not composed of, you're confused. If you have an infinite amount of water, you can still take out a finite bucket of water, okay?
Yeah, but the rest
Wait,
is still
can I ask
infinite.
you- Can I ask you a question?
cares?
About the infinite?
Are you asking me?
Yeah.
Yeah.
So there's the infinite monkeys theory of Shakespeare.
Sure.
So if there's an infinite number of universes, do you think there's a universe in which you won that debate against me earlier?
Stop.
No. Well done. You piece of work.
I retract the debate from the previous debate. I'm never gonna debate a server owner again in my life. It's too dangerous.
Damn straight.
Well, I would like to make it officially. I would like to challenge you, Mr. Slave, in a cordial and properly formalised debate on climate change, whether it's a hoax or not. Are you willing to take me up on my offer, and can Sea Lion provide the YouTube channel, perhaps, of which to do it? Are you up for it, Mr. Slave?
Of course. Of course.
All right, there we go. What happened?
Right.
Why would you be a climate denier, mate?
Why would I be?
Well, that's what we'll find out. We'll find out why he's a climate change denier.
There's basically the very long list why it's the correct position. Why it's my position. Very long list. I mean,
buddy.
In order to convince
keep it
me to not be a
Save
climate...
it for Boomer.
Okay, let's get back to look. The point is, people don't like the ether theory. Like when I mention ether, people lose their like shite. Let's say, to be family friendly.
Yeah, because there's competing hypotheses, and ether hasn't been validated. Relativity has been validated. It was validated using predictions based exclusively off that model, which means that there is evidence that positively indicates relativity that was predictive, whereas there's no positively indicative predictions made by the ether model. That's one of the main ways that we sort out hypotheses, their truth value when they compete. Do you understand that?
Yeah, I mean, you're repeating what quote unquote everyone says. So obviously,
Yeah, great. And you've got your own metric you go by. So I don't know why you discuss it with other people, because we have a fundamental difference in our metrics at the very bottom. So I don't know why you bother trying to come here to talk to us about contradictions or literally anything else when you don't even share the base epistemology in order to apply any judgment at all.
Well, obviously not in order to change anyone's mind. I come here to cross-examine my opinion. I just want to make sure that I'm correct within my own universe, So I'm just
Yeah,
looking.
but yours is purely based off vibes, mate. There's no concrete way for us to show that there's an internal critique with your view of reality, because your view of reality is just vibes. It's fluid. It changes all the time.
Well, you didn't contradict anything I said thus far.
People have. I've been here for people contradicting, showing that there's particles that have an energy signature that can't come from a wave.
Well, in my mind, no one has accomplished to change my mind, to contradict me
Yeah,
sufficiently.
we agree with that for sure. In your mind, you have never once been able to, because of your fluid epistemology that you created so you can never be wrong, had to confront the fact that for any actual epistemology that works in reality, you would have glaring contradictions, or at least no valid reason to believe that you're right about this ether model. I agree with that. We both agree on this.
Yeah, but you just personally attacked me, so please refrain from that. Don't be mean. I'm not here to
I
be
didn't.
attacked.
I
Yes, you did.
attacked your epistemology.
Look, you said that in my own mind I cannot be wrong. That's not nice to say. Please don't say that. Look, I'm
It
not
is the
being.
truth, though. If the truth makes you upset, that's a you problem, not a me problem.
Look, again, please don't attack me. I'm not here to be attacked. I don't attack anyone usually. Please stop it. Anyway,
If it makes you feel attacked, that I am telling you that you are wrong, and that is a you problem. Maybe stop being wrong.
please stop referencing me. Please stop talking
Okay,
about
great.
me.
How about this? Why don't you tell us, how about you tell us a way that I could tell if relativity is true versus your ether model?
There's no verses. We just finished saying there's no contradiction.
Can both hypotheses be true at the same time?
Of course.
They can. So wait, you're telling me that there can be this idea of like the constant of C, the particles, the idea of there being gravity as some stressor on space-time, as well as there being some fluid called the ether that must necessarily exist, and there's no space-time, and all of the interactions between gravity and particles of mass is just vibrations in the frequency of the ether. You're saying those two things those two hypotheses, those two theories can exist at the same time.
Basically, yes. I didn't follow exactly everything you said, but yeah, basically, yes.
They
You're welcome.
can't, because nowhere in relativity is there an ether substance that is the fluid that hits other things and explodes and causes motion or inertia on particles. It just doesn't exist in that model. So both models can't exist at the same time.
There's no contradiction. Find the contradiction.
Of course, there's contradiction. One model has something that is the ether that is an existing fluid, and the other one doesn't.
That's not a contradiction.
It literally is. It's one has something that the other does not. It's contradictory to think that those two can exist at the same time.
To say that 1 + 1 = 2, that's one theory, and 2 + 2 = 4, it's another theory. Those are not contradictory theories.
No, we're trying to explain the same phenomena. We're trying to explain why there are, of an apple in my hand and an apple in your hand, the amount of apples in both hands. We're trying to explain that phenomenon, not two apples in my hand, one apple in one of yours and one in the other, and then two apples on the floor, and then just arbitrarily choosing a collection of apples to add together for no reason. We're trying to explain the exact same phenomena, so the exact same reality we live in, with two competing hypotheses, where one has some major difference to the other, and you're saying that both can be true at the same time, despite that being a direct violation of like the law of logic, that something is itself and not something else.
So let's say GR, it's not a quantum mechanical theory. And my theory is the quantum mechanical version, or the lower level. So GR sits on top, and so does SR. SR and GR sit on top of my ether assumption.
Do SR and GR say that there is some fundamental fluid that causes particle-to-particle interactions or vibrations that cause all motion in the universe?
No. They're not.
Okay, does your theory say that? Okay, does your theory say that gravity is particles crashing into ether particles crashing into each other?
You could, yeah, you could say that, sure.
Okay.
Where's the contradiction?
And does general relativity say that? Does general relativity say that?
No, but they are complementary. My quantum
No,
gravity.
they're not. They're contradictions.
Where's the contradiction?
The contradiction is in general relativity, the inertia is caused by a bending of space-time causing a vector change to objects of mass because the mass distorts space-time. In yours, the motion of objects of mass is caused by some underlying fluid that is bashing into those objects of mass and for some reason attracted to the objects of mass, causing a differential in the pressure gradient of that fluid such that they keep bashing into those objects of mass. So in one, it is a particle-to-particle interaction causing the inertia to the acceleration in the vector, and the other, it's the underlying substance being warped, so changing its shape such that there's an acceleration and a vector put on those objects of mass. Those are two things that cannot be true at the same time. It is a contradiction to say both can be true at the same time. It's literally the law of logic that something can't be itself as well as something else at the same time.
No, so I'm producing a quantum mechanical theory that is that gives us the phenomenon of gravity, and then Einstein takes the phenomenon of gravity as a given, and he has a field theory about it. So I have a quantum mechanical.
Does general relativity say that the cause of the acceleration due to gravity is a change to space-time, and yours say that it is a fluid called ether fluid?
No. So GR doesn't say what the cause of gravity is. GR describes gravity as the bending or the curvature of space-time. It's just a description. There's no cause. There's no causality. There's no mechanism.
So the cause...
GR is not a...
So the cause is the stresses of mass on space-time causing space-time to bend and warp.
What causes
such that you get an acceleration. So the cause of the acceleration is the warping of space-time. In yours, the cause of the acceleration is the ether attraction, right?
Look, so I'm giving I'm giving a quantum mechanical cause and effect.
It doesn't matter if it's quantum mechanical or if it's like mechanical in space-time. That doesn't matter.
But you have to let me speak just a little bit once in a while. So
there's a snake in my house.
Oh, what type of snake?
Is it a
I don't know.
evil?
It's only like a foot
You're in
long.
Australia.
And
You got to be careful.
Hey, Trouble. I've killed 2 snakes this week. 2 king browns.
That's Satan coming for you, mate. You're doing the Lord's work.
King
Gone behind a bit of furniture.
Look,
people try to say they protect the animals. I say, fuck that. Get the shovel. Take its head straight off. No fucking around.
What sort of
Snakes
snake
have
is
no
it?
purpose in Australian outback or society.
Well, it's only a foot long. My cat brought it
Kill the
in, I'm guessing.
What a waste of time. There is contradiction. There's no contradiction. There's infinite. He just finished saying, "Oh, it doesn't contradict." That's what he said when I walked into the discussion. And he said, "Oh, ether. There's no contradiction. You can have an infinite number of theories, and they're all correct." Wait, what? And then he says, "No, there is a contradiction. Your ether contradicts." It's like he's the Heisenberg scientist. I am both contradicting and not contradicting, and it's not a contradiction to claim that. Wonderful. And they're all listening and laughing. Oh, I'm such an idiot. I'm such an idiot. I don't understand. I don't understand anything. Oh, it's so funny. We're so smart.
And found in just about every physics textbook, but it didn't seem to have much effect on Einstein. What made Einstein skeptical was another thought experiment. It's called the magnet and the conductor, and it appears in the first pages of his 19...
It didn't have any effect. He mentions it in the paper. Why would you say it didn't have any effect?
paper on special relativity. Imagine a conducting wire, just like the kind that bring electricity to your home, but formed in a loop.
It's in the same paper. You're quoting the same paper. He quotes the Michelson experiment without name.
Of course, everybody was interested in this question, and a number of experiments were designed to try and test whether or not the luminiferous ether exists. One of the most famous ones is due to Michelson and Morley and found in just about every physics textbook, but it didn't seem to have much effect on Einstein. What made Einstein skeptical was another
Why would you say it didn't have much effect?
thought experiment. It's called the magnet and the conductor, and it appears in the first pages of his 1905 paper on.
They both appear. They both appear. Here's the paper. Here's what you're discussing. This is what you're discussing. And here is Michelson and Morley. Unsuccessful attempt to discover any motion of the Earth relatively to the light medium. This is basically Michelson and Morley. They are side by side. This is these two asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. Right? That's basically what you're talking about. And it's side by side with the unsuccessful attempts to discover the light medium. Oh my God. And this guy's a professor teaching this. I really appreciate this guy, but oh my God. How could you be so wrong on this is your job. You get paid for this.
On special relativity. Imagine a conducting wire, just like the kind that bring electricity to your home, but formed in a loop, and suppose it's at rest in the luminiferous ether. Now imagine a magnet in motion passing through the center of that looped wire. According to the theory of electricity and magnetism, a new force will be created called the induced electric field, which pushes electrons around the wire, creating an electric current. Now this doesn't happen if the magnet is at rest. There's no induced electric field.
Einstein didn't feel that there was a contradiction to ether.
And there are no electrons pushed along the wire. And you might think that you could use these devices to determine what the ether state of rest is. I'll somehow rig up a device which has electricity moving on this wire exactly if the magnet's in motion with respect to the ether. What Einstein realized is that it doesn't work. No matter how hard you try, you can't use a magnet and a conducting wire to determine the ether frame of rest. Here's a simple way to see this. Suppose the magnet is attached to the conductor so that they both move in the same way. When they're just sitting there, there's no motion and there's no electricity on the wire. What happens when they start moving? As we've just seen, a moving magnet does create an induced electric field, a force that pushes the electrons along the wire. But another part of electricity and magnetism tells us that if we have a moving conductor through a magnetic field, it will produce a force in the opposite direction around the wire. The net result is no force at all, and so no electric current, exactly as if the two objects were at rest. That is, the theory seems to conspire to make it impossible for us to tell whether the two objects.
Yeah, the ether theory seems to conspire to not let us know that it's there. Well, there is a reason why that happens. What's the reason? What's the mechanical, right? When you say the theory seems to conspire to not let us know that it's there, I mean, that's incredible. So obviously that can't be. I mean, that doesn't make any sense. Why would a theory conspire to not let us know that it's true? So two things are compensating somehow. Let's listen to this again. From the beginning.
To the light possible if that were true. Of course, everybody was interested in this question, and a number of experiments were designed to try and test whether or not the luminiferous ether exists. One of the most famous ones is due to Michelson and Morley and found in just about every physics textbook, but it didn't seem to have much effect on Einstein. What made Einstein?
This is a Feynman diagram on a painting. Why is there a Feynman diagram on a painting? This is an electron and a positron exchanging a photon. But there's something else here. It's not good to debate people when they get you upset. That's not like if you're debating someone and they're getting you upset, then it's like, let it go. It's not worth it. Like these people, they keep attacking you. Once they attack you, let it go. They're not worth it. Why would you talk to people that are attacking you? That's not the purpose of any debate. As soon as they let go of the topic and they go to you, they come after you, let it go. Let them go. I I'm I go into these places to discuss things, to discuss my discoveries. So I show them black on white. Einstein didn't feel there's a contradiction. So he says, no, there is a contradiction. Well, Einstein didn't feel there's a contradiction. I don't feel there's a contradiction. If you feel there is a contradiction, I don't care. It's like you do you. Fine, go ahead. Do you want me to comment on the fact that you, however you feel? I'll comment, but I gotta let it go because people don't like losing debates. So a debate has its limit, especially with weak people that just don't want to lose. And then they project it to you that you don't want to lose. I really care. Like, why would I care? Why would I care if I lose? Like, I have nothing to lose. Well, no, you care. Anyway.
Skeptical was another thought experiment. It's called The Magnet and the Conductor, and it appears in the first pages of his 1905 paper on special relativity.
It's in the first paragraph. It's not in the first pages. Did you read it?
Imagine a conducting wire, just like the kind you bring electricity to your home, but formed in a loop, and suppose it's at rest in the luminiferous ether. Now imagine a magnet in motion passing through the center of that looped wire. According to the theory of electricity and magnetism, a new force will be created called the induced electric field, which pushes electrons around the wire, creating an electric current. Now this doesn't happen if the magnet is at rest. There's no induced electric field, and there are
Why does that happen? Why does a magnet moving through a wire induce an electric current in the wire? That's the question. What's the quantum mechanical explanation? And that quantum mechanical explanation will explain to you everything. So you don't need SR for this. This is nothing. Like, SR is the conclusion SR is the conclusion of quantum mechanics. SR is basically, what would you say it is? It's not a field equation, but it's the conclusion. It's based on an assumption. The assumption is itself a conclusion of quantum mechanical effects. This is, at the end of the day, it has to be due to quantum mechanical effects. So what are the quantum mechanical effects that we need, or what is the quantum mechanics that is going on here? Well, if we ignore the ether, then nothing makes any sense. How could you have a field? What is a field without the ether? So that doesn't make any sense. It's senseless. So we have to have an ether just for there to be a field, an electric or a magnetic field. A magnetic field is a metamorphosis of the ether. The ether changes. It deforms, as Einstein says. It curves. It physically curves. It changes. It suffers stresses due to this electric magnet. So the ether around the magnet is deformed in a certain way. It curves, right? We know that it curves. certain lines, as Faraday said, there's lines from the north to the south, lines of, he called it, I think, lines of force. It's difficult to say that there's a force there, but something, right? If we sprinkle iron chaff, iron powder, we will see these lines, that the iron will align along these lines. So something is there. When we sprinkle iron dust, we see something is there. You can't deny it. Something is there. So okay, so there's something there. The problem is, if there is an ether, so as the magnet is moving through the ether, the magnet, right, we know because of gravity, the ether is flowing very fast through the system. But this system doesn't seem to be influenced in any way. Well, it is. We know because of general relativity that it is influenced. So we actually know that it is influenced. That is general relativity. So that's incorrect. But let's for a second go into space so that GR is not going to bother us. Still, there is ether around us. Now, but we might be moving at incredible velocities compared to the ether. Still, we don't notice it. Yeah, because we are affected by the ether as we're looking at this. We are just as affected as it is, so we can never notice it. That's the problem. That's the conspiracy. So the ether conspired to not let us see it because everything is the ether. We are the ether. So as we're moving along with it, we cannot notice it. And if we're stationary and it is moving, then we do see it. We do see it shrink. We do see it. And that's what happens when the magnet moves and the wire is stationary. The wire is stationary, or relative to the ether, the wire, let's say, is more stationary, and the magnet is more moving more. So the magnet, let's say we're moving at some incredible speeds to the right. Right? This is a quantum, we're at the quantum level now. So at the quantum level, we are the observers, but we have the observer paradox that we are influenced by the same. It's good that I'm recording this. This is such a good explanation. I'm going to have to re-listen to this and write it down. This is so good. So this is a quantum mechanical explanation of why the ether theory conspires for us not to be able to detect it. Because we are, just as we move along with this system, we're just as influenced. We become entangled, as they say. We are entangled with the system, so we cannot notice, we cannot detect the motion through the ether because we're moving through the ether and we are just as impacted. We are electromagnetic creatures. We are just as impacted, and any apparatus we apply is just as impacted. So the ether is unnoticeable. And if we are not moving relative to this magnet, then it is noticeable. But then we say, but then we say, okay, but that has nothing to do with the ether because, well, but there has to be an ether because how else would you explain what is going on here? I mean, the only mechanical explanation is that there is ether. Otherwise, you don't have a quantum mechanical explanation. Right? In quantum mechanics, they would say that there is actual particle exchange. That there are photons. There's photons being exchanged. There's virtual particles. There's a quantum foam. There is something here. Even they agree there is something here. It's not vacuum. Okay, so we all agree. Just give it different names. So how could they not see it? How could they be so blind? Unbelievable. And I told him it's a mistake to debate a server owner. And he said, yep, don't debate me ever again because I will ban you. Basically, yeah, that's a bad idea. Never debate a server owner. Never, ever. That's like, unless you want to get banned. Anyway, so there are virtual particles coming in and out of existence, being exchanged, creating a flow. Something is flowing. There is emotion, not electrons. Electrons are not moving. Also, photons are not. Photons are electromagnetic. So it's not photons, but some sort of virtual particle. Or is it a photon? Maybe it is a photon. Right? Because right now, the north is attracted to the south. What is this attraction? Well, it must be particle exchange. They're exchanging particles, and that's causing the attraction. They're sucking in particles. Right? This guy's being pulled forward, and this guy's being pulled backwards. There has to be, right? This guy must be sucking in, and this guy must be sucking in something, because if we, it wants to fly off. If I put a magnet here, a south will be attracted. That means this it's trying to move into it. So this is south. So it must be attracted into this. And we know the path. We know the lines. What are these lines composed of? What is quantum mechanically, what is here? What are the quantum mechanical things? What quantum mechanical phenomenon is happening here? Is it dragging in photons? It's like this guy is dragging in photons and this guy is dragging in photons because they're both pulling each other. But if I throw iron dust on this thing, the iron dust is not going to get pulled because it's not magnetized. The iron is not magnetized, so it's not going to get pulled. It's just going to align. It's going to become magnetized just in order to get aligned. I mean, some of it will stick to this, and then they'll stick to each other, and they'll create a path, a line of force, a line of something. And the air is doing the same, but ultimately something underneath is doing this. Some fluid must be in here that is also through us. So we can't notice it. Whatever it will do to this, it's doing to us, so that to mask and hide itself. So, but this is the rubber ducky. As the rubber ducky is moving faster and faster through the water, its clock is ticking slower. As it's observing its friend, as two rubber duckies are moving through the water at the same velocity, they're observing each other's clock ticking normally. It doesn't matter how fast they go. And if they go faster than the speed of light, faster than the speed of the water waves, okay, their clocks are both going to be frozen. And when they're going to be thawed, they're going to look each other, and again, they never missed a beat. Wow, I'm becoming hungry, a little bit hungry. Fascinating. This is so fascinating. And Einstein didn't have this knowledge, but at the end of his life, he already had this knowledge. But he didn't go back to SR to fix it, to make it quantum mechanical, to explain it, to get rid of his postulate. Why didn't he go back to get rid of his postulate? Why didn't he go back to use the ether? Because his ether wasn't flowing. He fell into the trap of the curved space-time instead of the flow of the ether. Incredible. And I'm sitting here yelling this revelation, and all these guys, it's like, I mean, they care, but apparently they don't care enough. They're afraid of each other. They're like chimps. They need to be part of a group. Whatever the group does, they'll do. They need to be part of a group. They're afraid. They know how they mistreat anyone who doesn't belong to the group. So they don't want to leave the group. That's why it's important for them to abuse any outsiders. That's actual xenophobia. Interesting. Fascinating. Let's tell them.
It's laughable. They measure.
Great. So you agree we can detect CO2? We can measure CO2. CO2 exists. You've just great. You've learned something, Bartek. You just learned something.
Oh, they're debating climate change?
Significant. It doesn't exist.
Yeah, you learned something. Good job.
You see, they abuse each other. They're not nice to each other. They don't. It's nothing to do. It's just in-group, out-group preference. It's just tribalism.
Which one is it? You're flip-flopping, mate.
It's just chimps getting excited that they're part of a group.
Good job. It's measurable, but you said it can't be measured. Why are you flip-flopping?
Yeah,
What's
it's
going on?
stupid. It's literally retarded that we have to measure in parts per million.
Why?
Okay. Think about it.
I'm thinking hard.
Yeah,
My brain's
say going
rustling.
in, yeah,
Think
like
about
on
it.
ships and things like that, going into a closed tank. The gas measurements
You're an
are
idiot.
done. Yeah,
We
no,
don't
I'm not.
live in
You
enclosed
are
environments like tanks. We
Hey,
don't
can I?
Why
live
do
under the
they
ocean,
when?
dickhead.
So why do
We
they
don't live
measure?
in fish tanks.
Why
We live
do
in
they
environments.
measure the different
We
gases
open the
before they go
window.
into the tank? Like
We don't
CO2,
go into
oxygen,
tanks. We don't live
nitrogen,
in tanks.
Wait.
H2S, hydrocarbons.
Hey, can I
Why do they
interrupt?
do that?
Can I interrupt for a second? I'm not
You can try, Slave, but it's got to be interesting and on topic.
Okay, look. No, it's on topic. It's on topic. It's actually the way we're conducting these debates. So I was thinking about it. So
Right, knock it out. You got 15 seconds. Let's practice over.
So that's exactly my point. That I think we're being very violent towards anyone who seems to
But
be.
to get to your point, I mean, we were now in a discussion. Could you make an argument about what we were talking about instead of being long-winded about how people act or
Okay,
behave?
shut up. Shut up, Stefan. You're a retard. I don't want to talk to you.
Okay.
So-
Listen.
We talk to our fellow Aussies like this all the time. It's normal.
No.
So,
Like,
as I was saying,
no, wait one
when
second.
we have to measure something in parts per
Listen.
million in an enclosed environment, it's not even worth measuring. And if you're trying to equate living in fish tanks or in a fucking hull of a ship as an environment, you're a retard. We don't live in these environments. CO2 doesn't exist in the natural
Yeah, good job,
environment.
Lartec. You have confirmed CO2 does exist. It's just in very small amounts. So how can you, in the same sentence, say it does
It's
exist and doesn't exist? Isn't that an internal contradiction in the way you?
Okay, whatever. They don't want to talk. It's fine. Let's get back to the thing. I'm gonna need to take a break soon. This is really fascinating. Really fascinating. Because I'm able to imagine it on like in a mechanical way. So I'm looking at this. This is moving fast. We're moving fast through the ether. What do you expect there to? What's your expectation as we're moving fast through the ether? What should happen? Why should anything happen? I mean, the question is what causes this phenomenon of electric current? Why do electrons, right? Electrons start moving in some fashion, this way or the other way. They start moving around. So there's a force on this electron. Something is forcing this electron to move. What's causing this electron to move? But only when this magnet moves relative to this electron. So this electron, there's a single electron in here, a free electron, that it's noticing the magnet moving relative to it. How does it know? What, it has a radar? What, it's talking to it? How does it has eyes? How does it know? Right? So what does it mean for the magnet to move relative to the electron? Okay, so let's keep breaking it down, right? So as soon as we say electron, we're being quantum mechanical. Okay, let's go now to this electron, right? The whole thing is caused because there is a spinning electron here. A spinning electron induces a magnetic field. What does that mean? What is a magnetic field, right? So there's a spinning electron spinning with the vector is pointing to the right. That's what it means for there to be a north here and a south here, because the electron is the same way, pointing to the right. All the electrons are spinning and they are all aligned, pointing to the right. That's a magnet. So the electrons are all spinning towards the right. What does that do? What does a spinning electron do? Why does a spinning electron create a magnetic field? What is a magnetic field? A magnetic field, after all, doesn't exist. A magnetic field is an illusion created by an electric field. What? So the spinning electron is creating an electric field? Well, a spinning electron is an electric field. It's literally electricity flowing. That is a spinning this gives you a feeling for what the spin is. So there is a spinning electron, which is a wave. So there's a waving electron rotating or orbiting a single point such that the angular momentum is pointing to the right. So this waving spinning electron, it's a wave and it's spinning to the right. And it's spinning fast. So what if it's spinning fast? At the end of the day, the question is, what causes? Why does a spinning electron, right? So this is a tiny electric wire. There's just many of them. But these are all tiny electric wires. So all these tiny electric wires are always waving around. So there's always an electric current. So there's an electric current which produces a magnetic field, right? Tiny electric currents produce a magnetic field that we can see. So they must be spinning. There's no way around it. But these are waves. These are spinning waves. So a free electron feels like it's like a string, right? We know when it orbits the nucleus, it's basically it's a string. It's a closed loop of electric density that is waving in a circle. That's all it is. So maybe that's all it always is. It's always that. So it can grow to any size. When it's free, it can grow to any size. If it absorbs energy, it can wave in higher frequencies. Higher frequencies mean that it's longer, that it's bigger. It doesn't have an issue. But if it's a wave that is spinning around itself, so as it passes through the double slits, it's a spinning. Why is this spin intrinsic? Why is it always exactly, well, that has to do, all right, it never slows down. So it's intrinsic, but it is spinning. But what is spinning? There's no motion. It's the wave. There's a velocity of the wave. The wave has a velocity, and it's waving in the ether. It's waving in the ether, but it's interacting with the Higgs, so it's not waving at the speed of light. It's waving very slow, but it's waving. but it's a current. It's always a current. It's intrinsically a current. That is the definition of an electron. An electron is, it's very, basically it's like a tiny wire. It's a tiny virtual wire of pure electricity. Like when we see plasma, those are electrons. Those are many, 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 many of them. So all you have to imagine is that each and every one of them, it's a tiny plasma circuit of ether. It's a wave in the ether. It's a circular current in the ether. It just waves and waves. It's not moving. It's not actually, there's nothing spinning. The wave is waving in a circle, and the wave spinning has momentum and has mass. The whole thing has mass. So as the wave is waving, it's vibrating in the Higgs, within the Higgs mechanism. So the ether interacts with it and slows it down, but doesn't take away its energy. It doesn't slow it down. It just bounces back and forth. So it vibrates as, but all these things are intrinsic. So it has an intrinsic mass, and it has an intrinsic angular momentum. The angular momentum somehow never changes. It's intrinsic. It's built into the type of wave that it is somehow. There's no energy loss somehow. So it will forever spin around itself, this electron. And for some reason, that spinning, well, that's an electric current. And this electric current creates a magnetic field around this ring. So an electron is a ring. It's always a ring. And there's always, so it always creates a magnetic field. But what is a magnetic field? Well, an electron is actual electricity flowing, actual electric density waving in a circular pattern, in a ring pattern. And it has angular momentum. We know this. We know that we can change its angle. We know that an electric beam, an electron beam, we can change its trajectory using an electric field or a magnetic field. Okay. So it's creating, so really what we need is a quantum mechanical explanation of what's going on. All right, so what is going through, right? So let's take just one electron, one spinning electron here, and one spinning electron here. They're both spinning, but these guys don't have a preferred direction. These guys are all over the place. They're spinning every which way. It's not magnetized. These guys are all magnetized. They're all pointing in one way. So they're creating a magnetic field. What does that mean? What is a magnetic field? It's sucking in somehow virtual particles. It's creating photons. It's creating a disturbance. But if it's actually photons moving, that's an electromagnetic wave. That's not what we have. A magnet doesn't create an electromagnetic wave. No. It's the motion of photons. That's an electromagnetic wave. So what is going on? What is moving? Maybe nothing is moving? I don't know. Anyway, something, right? These lines. So there's lines that the entire universe is influenced by these tiny electrons, by this tiny electron. So this tiny electron is bending the entire universe because of its spinning somehow. But we know that this bending is an illusion, because this electron is not influenced by this if it's stationary. So it doesn't exist. But if this electron would be moving through relative to this, then this electron, suddenly it sees all these aligned electrons. Suddenly suddenly it sees all these electrons. Then it notices them. Then it notices that it's moving through a field, through a magnetic field. Well, it's just an electric field. We know that this is just an electric field. That's all that it is noticing, just the electric field. It's just noticing that all these electrons are inducing an electric field all around them. But as it's moving, this thing is becoming length contracted. As it's moving, it sees this thing length contracted. So what? Right? Because a magnet is not electrically, it's electrically neutral, but as it's moving, it sees the electrons, it sees it as electrically charged. If this is electrically charged, then this electron would be attracted. It's not attracted. It's going to move in a circle. But when we describe electricity, we're beginning to describe electricity on a quantum level. Right? We're saying this guy is seeing this guy, but that's not a quantum mechanical. That's not quantum field theory. We need to go to quantum field theory. The question is, what is the quantum field explanation of a magnet inducing a current? Okay, let's look it up. What is the quantum field theory explanation of basically induced induction? Quantum field theory visualized. No, I don't like it. Quantum field theory explained in 2 minutes. No, I want induction. How do you explain induction? 8 years ago.
Physics is a wonderful way for people to understand the world around them. It can explain how birds fly, why ice freezes, what makes fire glow, just to mention a few things. Now, this doesn't mean that the explanations are always easy and clear. In fact, the explanations can be downright murky for phenomena far from familiar. Perhaps the two physics theories that are the hardest to accept when you first encounter them are Einstein's theory of relativity and quantum mechanics. The first one talks about how moving clocks run more slowly than stationary ones, and how objects in motion appear to shrink. The second one tells us that no measurement is certain, and that probability reigns supreme in the subatomic world. Well, I'd like to tell you that there's some credible debate about these theories, and that we scientists have somehow figured out a way to return to the more intuitive physics of the late 1800s.
So everyone just assumes Einstein when they go into the quantum world. That's the reverse direction. You should go into the quantum world and come up with Einstein relativity, theory of relativity, from quantum mechanics. Quantum mechanics should give you special relativity, not the opposite. If you go the opposite way, that's like tying the horse in front of the carriage. Tying the carriage in front of the horse.
But that isn't true. The simple fact is that relativity and quantum mechanics have been tested countless times, and they work. Like it or not, we have to learn to accept these weird predictions are just simply true. However, and this might blow your mind, these ideas are also about 100 years old. Frontier science has actually moved on. What scientists currently think is even weirder still. So let's review a bit what traditional quantum mechanics is all about. It was invented in the mid-1920s, and it was exemplified by an equation devised by Irwin.
Just the opposite. Quantum mechanics explains everything. Why would you say anything is weird? There's certain experiments we can't explain, but in general, we're getting better at explaining everything. Like we have a mechanical explanation of like magnets and electricity. But why you could quantum fields be ether? Oh yeah. I heard him talk, and he said no for some bizarre reason.
Erwin Schrödinger, what we now call Schrödinger's equation. This equation explained why electrons had only certain energies and positions when they circled an atom. At its very simplest, the equation explained that an electron could be here or there, but never here nor there. That's what quantum means. There are certain discrete things that are possible in other.
That's not what quantum means. There's quantum weirdness is that little bit of the quantum realm that we don't understand. But in general, the quantum realm explains so much. To concentrate on the parts you still don't understand, that's like seeing the half empty glass. You have a half full glass that you can use. Instead, you concentrate on the half empty.
Others that aren't. Things that were quantized could be mass, charge, position, or energy. Now, Schrödinger's equation was only a partial quantum theory, and it didn't take into account relativity. What it did was take a proton and assume it was surrounded by a classical electric field.
It doesn't need to. You can start from quantum and derive relativity.
Now, remember that classical fields are not quantized. They vary smoothly. However, things changed in the late 1920s when Paul Dirac started puttering around with quantum mechanics. One thing he did was successfully merge quantum mechanics and Einstein's theory of special relativity. Another thing he spearheaded was a way to figure out a way to make a fully quantum theory. He did this by finding a quantum formulation of the electric field surrounding the proton. We call this the second quantization revolution. This just means that the electric field was expressed quantum mechanically, and that it joined such things as a quantum description of the location of matter, which was covered by the first quantum revolution. In the ensuing years, these ideas have been generalized to cover all of the subatomic forces, specifically the strong nuclear force, the weak nuclear force, and electromagnetism. While each force has a different precise formulation, they're all examples of what we now call a quantum field theory, or QFT. Although each theory has its own interesting peculiarities.
So QFT is the second revolution. So Dirac gave us QFT.
I want to talk a little about some general truths of all quantum fields. In modern physics theory, one can picture all subatomic particles as beginning with a field. Then the particles we see are just localized vibrations in the field. So, according to quantum field theory, the right way to think of the subatomic world is that everywhere, there are a myriad of fields, upward fields, downward fields, electron fields, etc. And the particles are just localized vibrations in the fields that are moving around. The idea can also explain how particles interact. For example, suppose you have an electron moving along. The electron is a localized vibration of the electron field. If the electron emits a photon, then the quantum field theory way of looking at things says that some of the energy of the electron field sets up a localized vibration of a photon field, which then moves away. So those are the essential features of quantum field theory. Theoretical physics simply imagines that ordinary space is full of fields for all known subatomic particles, and that localized vibrations can be found everywhere. These fields can interact with one another like two adjacent tuning forks. These interactions explain how particles are created and destroyed. Basically, the energy of some vibrations move from one field and set up vibrations in another kind of field. Now, of course, actually calculating something with this prescription is really, really very difficult. Math can be pretty crazy. But the basic idea is really very simple. If you look around you, and you have even the smallest ability to think creatively, you can imagine these vibrations everywhere you look. I don't know about you, but I think that's an awfully cool idea. Downright murky for a phenomena far from familiar. Physics is a wonderful way for people to understand the world around them. It can explain how birds fly, why ice freezes, what makes fire glow, just to mention a few things. Now, this doesn't mean that the explanations are always easy and clear. In fact, the explanations can be downright murky for phenomena far from the familiar. Perhaps the two physics theories that are the hardest to...
It's incredible how difficult it is to talk to people. So I would just say stay away from some people. Let's see what he says.
Was on Netflix, and I was...
Shut up. That's a terrible summary of my position. I won't debate straw man arguments. Not worth my time. um. So you agree that these are your positions. What do you mean straw man? I mean, do you disagree with anything I said? You're welcome to tell me that I'm wrong. What do you mean straw man? Do you disagree with anything I said? Yes or no? Let's debate. I promise to be civilized. Take a look at my channel. I am a model citizen. I never ever commit logical fallacies. I promise it will be fun and friendly as much as possible. Of course, it's not worth his time. He's a leftoid. So he didn't disagree with anything I said. He's like a panicist. Porn! Oh, porn! Porn! The universe is gonna blow up! Porn! Porn! It's like everything is a cause for panic for these people. Everything is a cause. The sun is rising. Oh, the sun is setting. Oh, the sun is in the middle of the sky. Oh, it's the middle of the. The universe. Like everything is the reason for these guys to become panicked. Like everything. It doesn't matter what. Everything is a cause for panic. These people are a panic looking for a cause. Oh my god. Oh my god. What is this certificate? I have a certificate. I have a certificate. I'm certified. Okay. Oh, be civil and respectful. Leftoids. Leftoids. I can't say leftists. Leftists are a panic looking for a cause. Leftists are a panic looking for a cause. Well, let's panic. Now, let's think of a cause why to be panicked. Scott Carney. I am Scott Carney. I am a genius. I am Jesus. Let's see. Investigative journalist, anthropologist, and New York Times best-selling author explores consciousness, history, climate, artificial intelligence, war, and most of all, truth. The truth! The truth! Substack, Patreon, homepage, Pokebear, LLC, Instagram, Twitter. You're on Twitter? Fox Topus, Wikipedia. Oh, Wikipedia. I'm on Wikipedia. I'm the best. I'm the best ever. I'm the best person ever. No one is as good as me. I am the best. Organ trafficking. Organ trafficking. Consciousness. The nature of enlightenment, cult psychology, the history of medicine, everything in between. New York Times best-selling author. Oh, everything is terrible. Greta Thunberg is the best. The good Jesus Thunberg. Wait, he has 91.5K subs? Wait a minute, what? I didn't notice that before. I thought it was like...
All right, so a few weeks ago, I was
Wow.
on Netflix.
So he's big. He's not small. I thought he's like 1.5. So all he has is that I'm strawmanning him. What do you mean? You asked me what I want to debate. What do you want me to say? What do you want me to say? Did he remove my comment? I doubt it. I wouldn't believe it.
All right, so a few weeks ago.
Where's... That's a terrible summary of my position. I won't debate strawman arguments. But where's my latest comments? Like with YouTube, it's so difficult to know what's going on. Top newest? It's gone. Oh, there it is. Your position is... Where's my response? Why is my response gone? Did he ban me? I don't know. Whatever. Let's get back. This guy. Okay, so... Let's hear it again.
The first encounter them are Einstein's theory of relativity and quantum mechanics. The first one talks about how moving clocks run more slowly than stationary ones, and how objects in motion appear to shrink.
Like Schrodinger's equation, that's like a guess in the dark. I would assume that at this point we have quantum field theory and it's more accurate than Schrodinger's equation. I would assume that we've gone into deeper layers. I mean, Schrodinger's equation is just like it's like an estimate. It's not accurate. You don't expect to get perfect results. It's just an assumption that the electron seems to be behaving like a wave. So let's project whatever we know about the electron onto a wave, onto the wave equation, and see what we get back. And we get stuff and we test it, and it has some accuracies. Sometimes it gives us good results. That's all. It's just a model. It's just a model of a phenomenon. Why are people getting so it's like what's this fascination with the wave equation? It's just it's just a mechanical explanation. It's just a simple model. It's just a wave model of a phenomenon. Really strange.
The second one tells us that no measurement is certain and that probability reigns supreme in the subatomic world.
No measurement is certain. Well, depends on what you're measuring. If you're measuring a wave, what does it mean to be certain of a wave? A wave is intrinsically dispersed. It's not clear what you're measuring when you're measuring a wave. I don't know. I don't know what, like, I have uncertainty as to what you mean when you say that you measure a wave. I don't know what you mean. I have uncertainty already. There's already uncertainty there. So, okay, so there is uncertainty when we measure waves. Okay. So that's not like something to be to to be excited about, or to be fascinated about, to be to 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 even talk about. She has a good body, but she's short. You can tell she's short because the proportion of the head to the body. The head is very big relative to the body. She's 5 foot, 5'1", 5'2".
And how objects in motion appear to shrink. The second one tells us that no measurement is certain and that probability reigns supreme.
Short people usually have good bodies because they're short, so they're wide, so they have wide hips. In general, they like tall people usually have, like tall girls usually have thin hips. They usually don't have wide hips. So they usually don't have as nice as bodies as. It's very difficult to find a tall chick with wide hips.
In the subatomic world. Well, I'd like to tell you that there is some credible debate about these theories and that we scientists have somehow figured out a way to return to the more intuitive physics of the late 1800s, but that isn't true. The simple fact is that relativity and quantum mechanics have been tested countless times and they work. Like it or not, we have to learn to accept these weird predictions are just simply.
What's weird? Why would you say anything is weird about any of this? I don't see the weird. The more I study this field, the less weird it becomes.
True. However, and this might blow your mind, these ideas are also about 100 years old. Frontier science has actually moved on. What scientists currently think is even weirder still. So let's review a bit.
Okay, so you're going to tell me that whatever they thought is weird, which I don't accept, and whatever now we are studying is even weirder still. Well, I know a little bit of what quantum field theory is. The last thing I would say is that it's weird. It's a very straightforward explanation of reality, of particles, particle exchange, gauge theory. Where is what's the problem? It's like mostly very logical, very reasonable, very explanatory.
Traditional quantum mechanics is all about. It was invented in the mid-1920s and it was exemplified by an equation devised by Erwin Schrödinger, what we now call Schrödinger's.
I mean, it's just an evolution. To stop at Schrodinger's equation to say it was invented, it evolved basically starting with, at the Big Bang. But Planck had a notion. Planck invented age, and Einstein noticed, like he came up with a particle notion of a photon, and de Broglie came with a wave notion of an electron. And then Schrodinger said, okay, let's dump all this knowledge, everything we know in physics, let's somehow dump it into a wave equation and see what that gets us. And since then, more and more people added more and more, right? It evolved. It's just an evolving and it's ever evolving theory. Why would you stop and say Schrodinger? Like, what do you want from Schrodinger all the time? Schrodinger, oh, Schrodinger. What do you want from him? It's really straightforward. I don't think Schrodinger thought of his equation as much as you're thinking of it. There's not that much to it.
This equation explained why electrons had only certain energies and positions when they circled an atom. That is very
I don't think so.
By Erwin Schrödinger, what we now call Schrödinger's equation. This equation explained why electrons had only certain energies and positions when they circled an atom. At its very simplest, the equation explained that an electron could be here or there, but never here nor there.
Okay. An electron is going to be there and there, but not at the center? I doubt it. Why do you say that? How do you know? I mean, Schrodinger is just an approximation. Schrodinger is just a model. Schrodinger is not Jesus. What do you mean it's not there? The probability, as you say, is very low, but it's never zero, right? You agree that the probability is never zero. right? You agree that the electron could be literally everywhere in the universe. So why do you say it's not there? 439 comments. Jesus Christ. 155. They contradict themselves. 155. Not there. All caps? No, just first. Not there, not here, not there. Okay. Not here, not there, right? Capital N, capital N. Okay. Not here, not there. That's it. That's absolutely incorrect. Incorrecto. Incorrectamente. Okay, that's incorrect. Why is it incorrect? The electron can be anywhere in the universe. We're not even measuring the electron. We're measuring. I mean, this is even according to the Born rule. Born interpretation. The electron can be anywhere in the universe with a low probability, But even that doesn't matter. Even that doesn't matter. I mean, how do you know that it's not there? I wouldn't even say it's incorrect. I mean, how do you know? What's your evidence? What is your? Have you ever looked? We can barely look in those in those regimes. What is your evidence? I mean, Schrodinger is just a model. It's a simplification. It's just a model. A model, 2 words. A model. A simplification. An approximation. Where an actual electron might be doing. It's just so you can't treat it like it's Jesus. I can't write Schrodinger again. Can't treat Schrodinger's equation. These people are terrible. Jesus said it's not here, not there. Okay.
There. That's what quantum means. There are certain discrete things that are possible and others that aren't. Things that are quantized could be mass.
Says who?
Mass, charge, position, or energy. Now, Schrodinger's equation was only a partial quantum theory, and it didn't take into account relativity. What it did was take a proton and assume it was surrounded by a classical electric field. Now, remember that classical fields are not quantized. They vary smoothly. However, things changed in the late 1920s when Paul Dirac started.
That's not true. He theorized that there's a waving electron, just like de Broglie, just a waving electron. There's electric density. I think those are his words. Tensors. Okay, we're doing tensors. What else are we doing? Quantum field theory. Quantum field theory. How does quantum field theory, how it gives rise to special relativity? How does quantum field theory create? How does quantum field theory give rise to special relativity? We didn't do much tensors, maybe a little bit. How does quantum field theory give rise to special relativity? Yeah, so from quantum field theory to special relativity. Mm-hmm. Okay.
Puttering around with quantum mechanics. One thing he did was successfully merge quantum mechanics and Einstein's theory of special relativity.
You shouldn't need to merge. You shouldn't need to merge them. You should be able to derive everything from quantum field theory. Why are you merging? At this point, that's fine, okay? Now come up with a theory that derives special relativity from quantum mechanics. I mean, why is that so difficult? Why am I able to at least think about it? I mean, an electron, I can build an atom. I can show you how an atom slows down. Right? An atom with or two electrons doing, right, quantum field theory, two electrons repelling each other through a boson exchange, through particle exchange, through a boson gauge theory. So they're exchanging virtual photons and repelling each other. But as you're moving faster, as these two electrons are moving faster and faster through the ether, right? These virtual photons, these are waves. These are waves. These waves move slower and slower. So the repulsion is weaker and weaker. Well, it's slower. Everything that these electrons are doing is becoming slower and slower. Right? If I have and that's a clock, right? Right? There is a rate at which two electrons are exchanging photons and repelling each other. But as these two electrons are moving faster through the ether, this activity, this rate drops. This rate is a clock. This rate drops. So the electrons should move closer and closer to each other. Well, the force of repulsion between that they're each feeling should be weaker and weaker as we're moving through the ether faster and faster. But how would we test it? Any apparatus would be experiencing exactly these same feelings. So so nothing can detect it. It's impossible to detect it. How would an electron detect? How would we detect time? Right? We want to show that the speed of light is a constant at the quantum level. So the speed of light is the interaction, is the photon exchange between two electrons. That's the speed of light. How would an electron measure the speed of light? How would we? So an electron needs to. So let's say we have an atomic clock or an electron clock that has 2 electrons. The emitter and the detector are 2 electrons, and they're exchanging a photon. As we move faster through the ether, that clock slows down. That interaction slows down. The electron waving through the ether slows down. Both electrons slow down their own spinning. Their spinning slows down. So their influence on the universe is diminished. But certainly, we observe their interaction to slow down. And that is special relativity from first principles. That's it. That's the answer. Okay, let's bring up the paper. Mr. Steve. This is 3.4? No, this is 2.4. How did it become 3.4? Maybe 3.1. Okay, so the next step is quantum mechanics. Well, it's going to be very similar. To this. We're going to restart the experiment at the quantum level. We're going to build an experimental rubber ducky that's composed of 2 electrons. Two spinning electrons. And we're going to show, right, they're repelling each other by transferring a virtual photon between them. And as we're moving faster and faster, this photon is moving slower and slower. So we see that the quantum mechanical interaction is slower. Everybody knows that. That's like, I'm not saying anything new, but now we see it quantum mechanically. And even the electron spinning is slower because it's a wave. We can even describe, we can explain that the electron now is spinning slower. Everything has slowed down. So that's 2 snapshots that we can create. Let's take, what do you want to take? I think it's a good idea to take, maybe start, I think we can just, we can talk about this. Or we can restart the experiment from scratch and say, let's start from a quantum-sized bathtub. Let's add a quantum-sized rubber ducky. It's going to have a clock with 2 electrons. They're going to be transferring a photon. Two free electrons repel each other. So they exchange virtual photons somehow. How do they exchange virtual photons? I don't know. But everybody knows they do. So I'm just going to exchange a virtual photon. It's going to go over at the speed of light through the bathtub, through the ether bathtub. Well, the second step after this, oh, I'm not sharing. Shoot, I hate it when this happens. So the second step, the second step. Let's start we can just have infinite diagrams. I don't want to have infinite diagrams. I just want to say that you could have this, we could copy this and go into the quantum realm. Okay. So this is going to be, well, what number are we up to? Let's go to the next number. So this is 3.1. This is 4.1. 4.1. So this is going to be moving to the quantum realm. So we're going to move to the quantum. In the quantum realm, what do we have? Moving to the quantum realm, 2 electrons exchanging a virtual photon. So moving the 2 electrons repelling each other by the exchange of a virtual photon. Right. So we have the same rubber ducky. The rubber ducky is now of quantum size. The rubber ducky is now of a quantum size. Rubber ducky, what's that? Rubber ducky at the time that the ticking is detected. So the rubber ducky, instead of, so to the wave emitter is now just an electron. Oh, this is 2. Three, the detecting electron for a photon, a virtual photon, is exchanged but we need to show that the electron feels that the speed of light is a constant. We just need to show that the electron measures the speed of light to be a constant. So again, the distance between them. So as far as this mechanism is concerned, the distance is a constant and the ticking is a constant. So the velocity of the exchange can never change. It's a constant. There's no way to determine velocity. There's no reference clock possible. Right? Now you understand that there is no reference clock possible. This is the fastest exchange possible. There's no way to have a reference clock. The reference clock ticks at the same rate. Therefore, the speed of light is a constant. A virtual photon is exchanged from, is exchanged. The conclusion is the velocity, the measured velocity from is a tick, right? This is the clock, and this is the distance. Again, the clock ticks at a constant rate. The clock never slows down. There's no reference frame to determine that the clock has slowed down. The moving ether. We didn't mention that there is ether moving. So this is going to be, this is 2. The quantum rubber ducky. Is moving through the ether. through the ether fluid. This is the introduction of, oh, we need to make a space, okay, through the ether fluid. So the rubber ducky is moving through the ether fluid. This is becoming 3. This is 4. This is 5. So the detector is also, so that's 2. 3. The wave emitter is now just an electron emitting a virtual photon. The virtual photon is a wave propagation in the ether fluid. The virtual photon is a wave, is a propagation wave. So a wave propagation is a propagation wave in the ether fluid. But the ticking has slowed down, but there's no way no one can ever tell. There's no reference clock to tell. Any reference clock will suffer the same consequences. So by all measurements, the time is a constant, therefore the length is a constant, the time is a constant, therefore the speed of the exchange is a constant. So we have space over here. I wish I could attach these points to something. This is, the rubber duck is quantum size. Okay, whatever. Okay. What? Hmm. Okay. All right, that's the rubber ducky. But that's not the wave. It doesn't wave in all 3 directions. And there's no way I can show. Yeah, there is a way. Where there's a will, there's a way. Oh, I can't magnify. Okay, I can magnify, but I can't. Come on. I can't capture. I can't. Okay, let's tab. That's it. Destroy it. Okay, we need. Oh, that's very good. Oh, but I'm limited in the size and the scope. Fascinating. Okay, I gotta run to I gotta run somewhere. You know where. You know where. Gotta run to the bathroom. Let me close and save. We'll come back to this. Let me play something. Let's play this guy. Okay. This guy. Let's see what he says. Intuitive? Intuitive a year ago? I don't think I ever watched that.
Like, but how did we go from these are Lorentz transformations, and this is how they look like. But how did we go from here to here? And what all of this mean? In this video, we are going to uncover the intuition behind these weird-looking transformations. But before we start with Lorentz transformations, we need to take a look what are the coordinate transformations in general. Every observer in a universe has a coordinate system, which means you can always measure the distances and time. Simply put, every observer has its own measuring apparatus and a clock. If there is a certain object in a universe, we can assign it the distance in space where it is located. Different observer, though, may do the same, but for him, his coordinates would naturally differ from mine. Now, I might wonder, what are his coordinates for this object in terms of my own coordinates? And since the second observer is not moving, the only thing I have to do is to subtract the distance of the second observer from my own coordinate, and I get the coordinates of this object in his coordinate system. If I make the separation 0, but I give the second observer some non-zero velocity, then this L is gonna be a function of time as the second observer is moving away from me. The distance he travels in the unit of time is just simply v times t. These you might recognize as the Galilean transformations. This set of coordinates tell you what are the coordinates of an object you observe for an observer that is moving relative to you with a velocity v starting at the same position at 0 time. So that was fairly simple and straightforward, right? But since we are using both space and time, it would be much more convenient to use space-time coordinates instead of just space dealing with time as a parameter that changes. Now in this space-time diagram, the points on this diagram we call events, and the objects are represented by world lines. If there is an object at rest relative to us at the distance x, then its world line is just a line in the direction of time. Now, if we start moving relative to this object with the velocity v, then the world line rotates, meaning we see the object moving with the velocity minus v relative to us, and we will cross it at this time. But now the important part began. Since I said that if you have a world line of an object, doing the Galilean transformations seems as a rotation in space-time, as the world line rotates for different relative velocities of the observer. But is this really rotation? Of course not, since we know that in Galilean transformations, the time is absolute for everyone, and therefore, if you have an event that is gonna happen in 5 units of time for an observer at rest relative to that event, then this is also true for the observers that are moving relative to this event. So it is not rotation, but it is a rotation and a stretch at the same time. This means that in Galileo relativity, we are all moving with the same speed through time, but with different velocities through space, which means that we are all moving with different velocities through space-time. But what if I told you that the reality is kinda different? that it is not the speed through time that is absolute for everyone. It is the speed through space-time that is absolute, which is the speed of light. The speed through time, therefore, have to be relative. This therefore means that if there are two events at the same position and you measure the 5 units of time on your clock between them, then you would read smaller time on the clock moving relative to these events. But now be careful, because this is just how you, as a stationary observer, experience this situation. We still have no idea how to transform these coordinates into a moving frame. So we don't know how this moving observer experienced this situation. All we can say is that when the second event happened, we read smaller time on his clock. We are still in the process of discovering the Lorentz transformations. Translating this to a simpler language, imagine this.
This has nothing to do with Lorentz transformations. Lorentz wasn't thinking about any of this. This is Einstein. Why do you call this Lorentz? All right, I'm gonna take a break. I'll be back. I guarantee it.